Houston, Texas, high noon. The sun here doesn't just shine, it presses down on your shoulders like a heavy, hot blanket. The air above the scorching asphalt shimmers with heat waves, and your lungs fill with a thick, distinct smell. A mix of heated rubber, dry prairie, and diesel fuel. I'm standing at the gates of the Genan plant, the world's largest tire recycling facility, and I can feel the soles of my boots starting to soften on the blistering Texas ground. Today, I'm not just a tourist. I'm a witness to a massive technological alchemical process, where what the world considers waste that won't decompose gets transformed into energy, and the very foundation of the highways we drive on. Houston didn't just greet me with sunshine, it slammed me with a wall of sticky heat that folks down here in Texas call the devil's breath. But the second I stepped through the entrance to Genan's facility, the sounds of the city, distant highway hum and rustling wind, instantly shifted into something far harsher. Industrial chaos. But chaos that's perfectly ordered, rhythmic, almost primal. The first thing that hits you isn't the sound, it's the vibration. You don't just hear it. It rattles your chest like a low bass line at a rock concert. That's the giant motors firing up the heart of the plant. And spread out before me are the real black Himalayas. Thousands, maybe tens of thousands of used tires stacked into neat but staggering mountains. Everything's here. Thin wheels from compacts that only ever touched smooth asphalt, all the way up to massive donuts from mining dump trucks, treads tall as a person. They all came here to die, so they could be born again. The smell here is something else. It's not just the stench of rubber. It's a complex cocktail of heated polymer, traces of road tar baked into the treads, and hot metal. The Texas sun mercilessly scorches these black surfaces, and the heat radiating off them makes you feel like you're standing next to an open oven. The air between the mountains has solidified. It's thick and oily. I watch as another truck rolls up. The hydraulics groan as the bed lifts, and hundreds of tires tumble down with a muffled rumble. Thump, 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 cascading to the foot of the black mountain. This sound of rubber hitting rubber layers over that same endless vibration from the plant's engines. It creates this uncanny sensation of being inside a living organism. The plant breathes with this rhythm. It's hungry, and these mountains are its food. The vibration intensifies when the feed conveyors kick on. You see these massive manipulators, like the claws of prehistoric monsters, tearing into the piles, snatching their prey. In this place, on the edge between old junk and raw material, you feel tiny. We're following the conveyor belt that leads straight into the heart of the main floor. Here, that vibration I mentioned earlier transforms into physical force, pounding against your eardrums. We approach it, the primary shredder. If those mountains of tires were a graveyard, then this machine is the industrial meat grinder that knows no mercy. The first thing that hits you is the contrast between speed and power. You'd expect the shredder to spin at breakneck speed, flinging chunks of rubber in every direction like a blender. But no, the shredder's shafts move slowly, almost lazily. But within that slowness lies colossal torque, force capable of crushing stone. It's a deliberately engineered method. Low rotational speed prevents the rubber from overheating, keeping it from melting and sticking to the blades, which would turn the machine into a gummy trap. When the next tire, say, a massive wheel from a Texas pickup, hits the rollers, something happens that makes you flinch. The tire tries to hold its shape. Its steel belt, that same skeleton that carried tons of weight on the road, puts up one last fight. But hardened blades made from special alloy dig into the tread like the teeth of a prehistoric predator. 1 second, and you hear that distinctive crunch as the steel wires inside the rubber snap under hundreds of tons of pressure. In that moment, bright, angry showers of sparks fly out of the shredder's jaws. It's the friction of the steel belt against the blades, creating miniature lightning bolts inside the machine's dark belly. The heat here becomes almost unbearable. If it was just hot outside in Houston, near the shredder, the air heats up to a temperature where the sweat on your forehead instantly turns sticky with rubber dust. You can smell the frictional heat, sharp, metallic, with notes of burnt sulfur. It's the smell of matter being physically destroyed. Dust is everywhere here. It's not just floating in the air, it's dancing in the beams of industrial lights, settling on every surface like black velvet. These are tiny rubber particles released during the tearing process. You can see chunks falling from beneath the rollers onto the exit conveyor. This isn't a tire anymore. These are shapeless, torn scraps of rubber, roughly the size of an adult man's palm. Mangled strands of steel wire stick out from them, those same cord fangs that magnets will pull out in the next stage. The chunks of shredded rubber that just passed through the shredder's jaws move along on the conveyor belt. They look terrible, torn, dirty, hot, with those same mangled steel wire threads, cord fangs, sticking out from every black edge. Right now, one of the most cinematic stages at the Genan plant begins. We're approaching the magnetic separation zone. Above the conveyor, where chunks of tires race by in an endless stream, massive blocks hang suspended, overhead electromagnetic separators. They hang low, almost touching the black flow, humming with voltage. What happens on the belt resembles an uprising of the dead. When a ragged chunk of rubber enters the magnet's zone, the steel threads inside it react instantly. You see it with your own eyes. Metal wire that a second ago was part of a solid framework suddenly comes alive. With savage force, it tears free from its rubber prison, dragging the entire chunk with it, or simply slipping out like a knife through butter. Metal literally shoots upward, defying gravity. It looks like strange, aggressive magic. Thousands of steel needles and twisted wires slam into the magnetic belt with a loud crash, spinning perpendicular to the main conveyor. This is that endless clacking, the sound of thousands of metal fragments hammering into the separator's steel armor. The heat in this zone is unique. The magnets consume a massive amount of electricity and generate heat themselves, mixing with the warmth from freshly cut rubber. You're standing in a cloud of a specific smell, a blend of ozone, which always accompanies powerful electromagnets, and warm, raw metal. It's the smell of a forge, but without fire. Look to the left of the main conveyor. Another mountain is growing there, a mountain of pure steel. The magnetic belt carries the captured metal beyond the rubber stream, and, where the magnetic field vanishes, dumps it into a separate hopper. You're looking at springs coiled into spirals, long sharp needles, tiny metal chips. Everything gleams under the factory lights with a cold, bluish glow, contrasting sharply against the matte black of the rubber. Stripped of its steel skeleton, the rubber moves forward into the darkest and most airtight section of the plant. Now that the metal's gone, the rubber chunks look surprisingly light, but that's just an illusion before the final battle. We're entering the secondary granulation zone. High-speed granulators transform the torn pieces into perfect rubber crumb. The air here is thick with black snow, fine dust swirling through beams of light. Each granule passes through a system of vibrating screens, where they're sorted by size down to a fraction of an inch. But the real climax lies ahead, inside the sealed steel pyrolysis reactors. We approach the long, insulation-wrapped cylinders. This is the zone of quiet energy. There's no open flame here, but inside, hellish heat reigns, 850 degrees Fahrenheit. The key secret? Total absence of oxygen. The rubber doesn't burn, it distills. Let me show you something incredible. This is a substance that weighs more than lead, gold, or any other metal on the periodic table. We're in Oregon, at a unique facility where they purify and process osmium. It's the 76th element that most people have never heard of in their lives, and that's a real shame. Osmium is like the introvert of the chemistry world. It's so rare and specific that most people simply don't encounter it in everyday life. This is extreme physics at its finest. Ready to see this cosmic stuff with your own eyes? Then let's go inside. First thing they told me walking in, don't touch anything with bare hands. Not because it's expensive, though it's expensive too, but because osmium in certain forms releases a compound that irritates mucous membranes and in sufficient concentration can damage your retina. It's called osmium tetroxide. So everyone here wears gloves, and the ventilation here is more serious than in a hospital wing. Great way to start a tour, right? But I'm already inside, cameras rolling, and there's no backing out now. Wish me luck. Now for the numbers, because without them, I don't understand why anyone would even mess with this stuff. Osmium melts at 5,486 degrees Fahrenheit. It's the highest density of all known elements. A matchbox with a volume of about 3 cubic inches, if you made it entirely from osmium, would weigh around 12 pounds. 12 pounds. That's like a small bag of groceries, only the size of your palm. I held a sample like that once. The feeling's bizarre. Your brain's telling you something this size can't weigh this much, but your hand's absolutely not buying it. It's one of those moments where the number in the textbook and the actual sensation in your palm are two completely different things. Another number worth keeping in mind, osmium's melting point, 5,521 degrees Fahrenheit. It's the third hardest metal after rhenium and tungsten among refractory elements, way higher than steel, which melts somewhere around 2,000 degrees. In practical terms, you can't melt osmium in an ordinary industrial furnace. Period. That's why they don't make ingots here, and they don't cast parts like at a regular metallurgical plant. The whole process takes a different route. More on that in a bit. Where does osmium come from? You don't find it like iron. No quarries or mines. Osmium's a byproduct of processing nickel and copper ore. Deep in the mines of South Africa or Canada, they're extracting nickel ore, and osmium just happens to be present in trace amounts alongside platinum, palladium, and iridium. Concentration, 1 to 10 parts per billion. To get a single pound of osmium, you need to process 500 to 1,000 tons of raw ore. That's why the market price sits between $1,500 and $2,000 per troy ounce. For comparison, gold currently runs just over $2,000 per troy ounce. Osmium is nearly neck and neck with it price-wise. The raw material arrives at this facility as osmium-bearing concentrate, a grayish-black powder packed in sealed stainless steel containers. The containers are small, about the size of a coffee can. Inside might be 2 to 5 troy ounces of material. Each one of these cans represents $3,000 to $10,000 of raw material. They arrive in a regular courier van, but with paperwork running several pages and cargo insurance. The exact amount isn't disclosed publicly, but from the manager's expression, it's clear the figure is substantial. And a small sample taken for incoming analysis. Literally a few milligrams of powder that go into a spectrometer. If the composition doesn't match the documentation, the batch gets returned. No discussion. First purification stage, dissolution. The concentrate goes into a reactor with an acid mixture at around 350 degrees Fahrenheit. Osmium converts to gaseous tetroxide during this process, the very compound they warned me about at the entrance. This gas is immediately captured and absorbed by a specialized solution in a sealed tube system. Zero external leakage. The system gets checked for integrity every morning before startup. Next, chemical reactions convert the osmium back into solid form and store it as what's called osmium sponge, a porous dark powder containing approximately 95% metal. This whole process takes 6 to 10 hours per batch, and there's no rushing it. The reaction proceeds at its own pace, and nobody tries to speed it up. The second stage is hydrogen reduction. The osmium sponge gets placed in a tube furnace, through which hydrogen is passed at a temperature of 1100 degrees Fahrenheit. The hydrogen picks up residual oxygen impurities, and what comes out is metal powder with a purity of 99.9%. This takes another 4 to 6 hours. The tube furnace looks completely ordinary, a metal tube about 3 feet long, hooked up to a gas line. If you didn't know what was happening inside, you'd think someone was just drying laundry. But inside this tube, the powder transforms from a dirty concentrate into one of the purest metals produced commercially in the United States. Stage 3 is pressing and sintering. The powder gets loaded into a steel die and pressed at roughly 3,000 pounds per square inch. You get a small cylinder, about an inch in diameter and half an inch tall. Looks like a coin, only thicker and darker. Then this cylinder goes into a separate furnace, this time at 2,000 degrees Fahrenheit, where the powder particles fuse together into a solid metal. After sintering, the density of the sample is already 22.5 grams per cubic centimeter, very close to the theoretical maximum for this metal. Shrinkage during sintering runs about 15% of the original volume, and you've got to factor that into your calculations ahead of time, because the die has to be created with extra room for exactly that shrinkage. After sintering, each sample is weighed and measured. Weighing here isn't just a formality. The scales are accurate to 1,000th of a gram, because at these metal prices, losing even a few hundredths of a troy ounce is real money. All trimmings, all leftover powder, all fine dust from under the press, collected and returned to the recycling loop. Nothing gets thrown away. Even the wipes used to clean work surfaces go to regeneration. They might contain a few micrograms of metal too. Where does finished osmium go? One application: nibs for premium fountain pens. Osmium is incredibly hard and wear-resistant, so a pen like this can write for decades without noticeable tip wear. That's why you'll see Oz marked on expensive pens next to the manufacturer's name. Another application: electrical contacts in relays and measuring instruments, where you need longevity through millions of cycles, and where ordinary copper or silver wears out faster. And the third area, one they talk about more carefully here, medical implants. Osmium combined with iridium creates an alloy of exceptional hardness, used to make pacemaker components and certain orthopedic devices. The human body barely reacts to this alloy. It's biologically neutral, which in medicine is extremely expensive in the most literal sense. The details of contracts with medical manufacturers, those aren't disclosed here. I asked how much finished metal they produce per month. The answer: 20 to 50 troy ounces. That's 4 to 10 pounds of metal over 30 days of operation. Sounds ridiculously small. But in terms of value, $30,000 to $100,000 monthly from a single facility of this size. And there's a backlog of orders 3 to 4 months out. Demand is steady. Supply is limited by nature itself. There won't be more ore, and the number of facilities worldwide that actually know how to handle this metal properly, you can count them on one hand. What do you think will happen when osmium runs out? Drop a comment, because I can't stop thinking about it. But your hand feels something fundamentally different from anything I've held before. Your brain refuses to believe it, but physics doesn't ask permission. That's the whole difference between knowing the number and feeling it in your palm. 12 pounds in your fist, and 0 special effects. Thousands of planes, just sitting in the desert. They'll never fly again. But each one, millions of dollars being carefully stripped away, bolt by bolt, right now. One engine, 30 million. Business class seats, a few thousand each. Even the coffee maker from an old Boeing gets auctioned off. People think aircraft boneyards are graveyards. But the truth is, they're the most profitable recycling operations on the planet. Today, we're going where almost no one gets to go. To watch a 150-ton giant get torn down to scrap metal in 30 minutes. And why this isn't the end at all. It's a whole new beginning. Why the desert? That's the first question that pops up when you see these thousands of acres packed with plains. It's pushing 100 degrees Fahrenheit out here, and the humidity's basically 0. Perfect conditions to keep metal from rotting and rusting. Planes can sit here for decades and still look like they rolled off the tarmac at JFK yesterday. But not all of them are here to die. A lot are just waiting for better times. The airplane recycling process starts with what the pros call harvesting. This is the most profitable part of the job. When an airline decides a plane is no longer flight-worthy, engines are the first things to go. One of those engines can run anywhere from $10 to $30 million in working condition. They're pulled using special lifts and shipped off for diagnostics. Even if the airframe itself is old, those engines can keep flying on other aircraft for years to come. It's like a heart that keeps beating in another body. Besides the engines, they remove the auxiliary power unit. That's a small engine in the tail of the plane that provides electricity when the main motors are shut down. That thing's worth serious money too. Next, we step inside the cockpit. For aviation fans, this is like Aladdin's cave. There are hundreds of switches, screens, and computers. Each black box or navigation instrument can fetch several thousand or even tens of thousands of dollars on the secondary market. Workers remove all the equipment very carefully, pack it into special anti-static boxes, and send it for testing. Same goes for the passenger cabin. You'd be surprised, but even the seats have value. A set of business class seats can be sold for several $1,000s to private companies or movie studios building sets. Galleys, meal carts, even coffee makers, everything goes up for sale. There's nothing worthless on a plane until it's just an empty metal tube. Once everything valuable is stripped out, the environmental specialists step in. An aircraft is a complex machine packed with hazardous fluids. Every last drop has to be drained. The fuel tanks of a large plane can still hold several hundred gallons of kerosene that can't be pumped out during normal operations. Hydraulic fluid also needs draining. It's highly toxic, along with lubricant from all the mechanisms and antifreeze. Just imagine, the total volume of all these technical fluids can reach 500 gallons. All of it gets drained into special tanks for proper disposal. Workers also remove batteries, fire extinguishers, and oxygen cylinders. If even one of those cylinders stays inside when the heavy machinery moves in, it can explode with the force of an artillery shell. When the plane becomes completely clean, the most spectacular part begins, destroying the fuselage. Here we see a giant excavator at work, but instead of a bucket, it's equipped with hydraulic shears. They're sometimes called the guillotine. The operator of this machine is a true master. He drives up to the aircraft and starts chomping off pieces of the wings. The sound is like someone tearing open a giant soda can, only 1,000,000 times louder. The metal crunches, cracks, and gives way under pressure of several thousand pounds per square inch. First they cut off the wings, then the tail section. All of this is done according to a specific plan, so the structure doesn't collapse onto the machine itself. Next, the excavator tackles the fuselage. It simply slices this massive steel tube into chunks about 20 feet long. This is done so these pieces can be loaded onto regular trucks and hauled to the metal mill. Watching what was once a majestic airliner that flew at 30,000 feet get turned into a heap of mangled metal in 30 minutes. It's a sight that makes you think about how fleeting time really is. But the equipment operators don't have time for philosophy. They need to sort the scrap as fast as possible. Sorting is the key to profit in this business. An aircraft is made up of different metals, and they can't be mixed. About 80% of the weight is aluminum, but it also comes in different grades. The skin is one alloy. The structural beams inside are another. There's also titanium, which is used in high temperature areas, like near the engines. Titanium costs several times more than aluminum, so there's a real hunt for every piece of this metal. There's also steel in the landing gear, and some copper in those leftover wires that couldn't be pulled out by hand. Workers use magnets and special scanners to separate these piles of metal. A lot of people think aircraft scrap is the end of the story, but it's actually the beginning. The aluminum from these planes, it's the highest quality metal. They melt it down at around 1200 degrees Fahrenheit and make new ingots. From that aluminum, they can then make just about anything. Beer cans, parts for new cars, or even new aircraft. It's a closed loop where nothing goes to waste. Experts say roughly 95% of a modern passenger jet's weight can be recycled and used again. That's an incredible number for such complex machinery. Here's a fun fact for those who love numbers. In 1 year at a boneyard like this, they can completely dismantle up to 200 aircraft. If you take the average weight of each at 150,000 pounds, that's 30 million pounds of metal going back into the economy. This is a billion-dollar business, and it's only growing because airlines are trying to upgrade their fleets faster to more fuel-efficient models. Older planes become too expensive to maintain, so they end up right here, under the Arizona sun. There's always something a little sad about watching planes die, but at the same time, I'm blown away by how incredibly organized this whole process is. There's no chaos here. Every swing of the excavator, every step a worker takes with a wrench in hand, it's all calculated down to the second. This is a massive machine that converts the past into the future. We've just watched hydraulic power transform a symbol of technological progress into raw material for new achievements. And even though these aircraft will never take to the skies again, they live on in the things we use every day. As we walk across this yard, there's a constant crunch of broken glass and insulation debris under our feet. The air smells like hot metal and dry grass. It's a unique atmosphere that's tough to capture in words. This is where engineering genius meets inevitable destruction. But it's not destruction for destruction's sake. It's destruction for the sake of creating something new. And that's really what our civilization is all about. We're constantly recycling the old to build something better, faster, and more efficient. I hope you enjoyed peeking behind the fence of this aircraft graveyard with me. Now, next time you're flying off on vacation, you'll know what awaits your plane in 20 or 30 years. And it's not scary at all. It's just another chapter in the life of metal and technology. Thanks for watching my explorations. Hit that like button if you're into massive machinery like this, and subscribe so you don't miss new journeys to the most fascinating places on our planet. We'll find plenty more spots where metal tells us its incredible stories. See you in the next video, where we'll tear apart something just as epic. Bye. Right now, beneath our feet, millions of dollars in platinum, through which liquid stone flows at 2,000 degrees. This is a factory where sand transforms into fiber thinner than a human hair, and somehow comes out stronger than steel. Most people think the most valuable thing here is the giant furnace, but they're wrong. The most expensive part is the invisible chemistry, without which the entire material literally crumbles to dust in seconds. Every factory guards this recipe like a military secret. Without it, there'd be no modern yachts, no wind turbines, no airplane fuselages. Today, we're going where outsiders aren't allowed. And the strangest part, we're saving for the end. The whole process starts with a pile of sand and rocks. They use pure silica sand, limestone, and kaolin clay. We're talking massive volumes. Every single hour, they dump tens of thousands of pounds of this mixture into the furnace. For anyone searching for fiberglass manufacturing technology, understand this. It's not just melted glass. It's a strict chemical formula where every percentage point of borates or calcium determines whether your future boat falls apart in the middle of the ocean. These ingredients get mixed in giant hoppers and fed into the furnace, where absolute fiery chaos reigns. The temperature inside that furnace hits 2,500 degrees Fahrenheit. It's so hot that if you threw a chunk of scrap steel in there, it would vanish faster than you could blink. The glass becomes liquid like water and starts glowing with a blinding orange light. Right now, we're standing next to the main source of danger. This furnace runs non-stop for years. The furnace walls are made of special refractory brick that slowly dissolves into the molten glass. Imagine living in a house that you're slowly eating yourself. After 3 or 4 years, they have to rebuild the entire furnace, and that costs a fortune. But the real magic of this plant is hidden below. Underneath the furnace, they've installed plates called bushings. These are the most expensive pieces of hardware you'll ever see in any industry. Each plate is made from an alloy of platinum and rhodium. Why not steel? because any other metal would simply dissolve in the hot glass or oxidize within hours. A single one of these parts can cost more than $200,000. The plant has hundreds of them. That means right beneath us, there are millions of dollars worth of precious metals with molten rock flowing through them. Each platinum plate has thousands of microscopic holes. When the liquid glass passes through them under pressure, it comes out in thin streams. And this is where the coolest stage begins, the pull. These streams don't just fall down. They're caught by a winding machine spinning at over 60 miles per hour. The glass is pulled so fast, it becomes 10 times thinner than a human hair before it even has time to cool. If you search online for how fiberglass is made, you've seen these shiny threads, but feeling their speed in real life, that's a whole different story. Here's a huge problem right at this stage. Thin glass is an incredibly brittle material. If these strands just touched each other, they'd instantly grind apart and turn into dust. So while the strand flies from the bushing to the spool, it needs to be lubricated. Every fiber gets coated with a special chemical solution. This is each factory's secret weapon. This solution protects the glass from self-destruction and lets it bond with epoxy resin later. Without this chemistry, fiberglass would just be a pile of useless glass garbage. Now we're watching thousands of strands gather into one thick yarn called roving. A single spool like this can weigh 40 pounds and hold tens of miles of continuous strand. Look at these rows of machines. They run around the clock, creating material for wind turbine blades, yacht hulls, and aircraft parts. The scale of production here is mind-blowing. In a single day, this factory churns out enough fiber to wrap around Earth's equator several times. A lot of people ask why fiberglass is so strong. The secret? Glass in fiber form has no micro cracks like regular window glass does. It's pure molecular strength. Take a bundle of this fiber 1 inch thick, and you could lift a truck with it. But working with this stuff is a serious challenge. Glass dust is constantly floating in the air. Walk in here without protective gear, and within 5 minutes, your body starts itching like you fell into a patch of stinging nettles the size of a house. The workers here are used to it, but for a newcomer, it's a real test of endurance. Once the spools are wound, they're shipped to massive drying ovens. That's where the threads fully harden and the chemical protection bonds to the surface. Temperature inside those dryers? 280 degrees Fahrenheit. It's a long haul, 12 to 24 hours. If moisture gets trapped inside a spool, all bets are off. Mold, total loss of strength, you name it. For anyone interested in fiberglass construction, here's what matters. This material doesn't rot, doesn't rust. That's why shipbuilders love it. When you see enormous sheets of fiberglass cloth laid into molds for future vessels, you get why this factory matters. Without these thin threads, we'd still be building heavy, clunky structures out of metal that's terrified of every drop of salt water. The production cycle at this facility is a continuous flow of energy and materials. Every minute the furnace runs costs hundreds of dollars in gas alone. Now add the cost of maintaining platinum bushings and the salaries of specialists who know how to tame molten rock. This is an extremely high-stakes business. Any mistake in the glass formula will cause the strand to start breaking. If a break happens at 60 miles per hour, it creates a massive tangle of filaments that has to be cleaned up by hand, shutting down the entire line. Right now, we're passing the shop where fiberglass is chopped into small pieces 1 or 2 inches long. This chopped fiber is added to plastic to make it stronger. It's used to make parts for your cars, appliance housings, and even smartphones. When you're holding a tough plastic object, chances are there are thousands of tiny glass skeletons hiding inside it, made right here. At the end of our tour, we see the finished goods warehouse. Thousands of pallets stacked with gleaming white spools. They look absolutely peaceful, but inside each one lies the energy of a blazing furnace and the precision of precious metals. This production isn't just industry, it's the triumph of human ingenuity over raw matter. Turning sand into fabric that can withstand ocean pressure or open sea wind. That's what makes me marvel at these plants every single time. If you Google fiberglass applications in industry or fiberglass properties, you'll find thousands of pages of text, but nothing replaces that smell of hot glass and the feeling of static electricity coursing through your entire body on this factory floor. This is where the future of our infrastructure is born. I'm thrilled we got to peek inside this closed-off world. Fiberglass manufacturing remains one of the most secretive industries because every plant guards its own glass recipes and chemical coating formulas. It's a world of big money, extreme temperatures, and massive risks. But it's thanks to this insane process that we have lightweight cars, fast planes, and reliable buildings. I hope you enjoyed this walk through fire and platinum. We saw stone become spider silk and learned why it's so brutally difficult. Make sure to check out my other industrial deep dives where we break down the most fascinating factories on the planet. It was lively, it was scorching, and it was incredibly eye-opening. Thanks for taking this journey with me. See you on the next tour, where we'll find something else massive, complex, and absolutely one of a kind. Stay safe and keep away from molten glass unless you've got yourself a shiny silver heat suit. Worth mentioning here, a lot of people are curious about fiberglass for insulation or making composite materials, and this plant is the very first link in that entire chain. Every composite starts right here, at the platinum bushing beneath that blazing furnace. Without this foundation, there'd be no space rockets, no modern construction. See you in future videos, where we'll unlock the secrets of other off-limits facilities. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, no human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete, containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions. Underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive upfront, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Jonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Jonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Jonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Jonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centres, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Today, I dragged you to a place where the transparent skeleton of our cities is born. Have you ever wondered how an ordinary pile of sand transforms into massive glass panels that hold back the wind on the 100th floor somewhere in downtown Chicago or New York? It's a genuinely cool story about how we learn to tame fire and sand to make things that look fragile but can actually withstand the impact of a small truck. We're at a super-strength glass manufacturing plant, and there's real industrial energy all around us here. Forget about that brittle glass that shatters from an accidental breath. Today we're talking about a material that's the foundation of modern architecture and safety. It all starts with something really simple that you see under your feet at the beach, but with one critical caveat. The main ingredient is quartz sand. But this isn't the sand you wiggle your toes in on vacation. Here it goes through such intensive purification that it becomes purer than your thoughts on the first day after payday. Besides sand, they add soda ash and limestone into this massive steel mixer. Soda ash is needed, so the sand starts melting at a lower temperature, while limestone makes the finished glass resistant to water and chemicals. If we used sand alone, we'd need the energy of a small sun to melt it. But this way, we cheat a little. They also throw in cullet, old chunks of glass that have already served their purpose. This saves a ton of energy and money, because melting an existing structure is way easier than turning stone into liquid from scratch. This entire mix weighs hundreds of thousands of pounds and gets poured into gigantic concrete bunkers, where the big journey begins. Now we're approaching the hottest point of our journey, the furnace. This is a massive structure as tall as a 3-story building that runs non-stop for years. If you shut this furnace down even once, it would simply destroy itself, because the molten mass inside would solidify and tear the walls apart. Inside, it's a real inferno. 2,900 degrees Fahrenheit. It's so hot that if you stood nearby without special mirrored protection, your eyebrows would vanish in a second. Natural gas roars in the burners, creating an incredible noise that vibrates your bones. The mixture of ingredients slowly transforms into a viscous, fiery liquid that looks like super hot honey or lava from a volcano. This liquid slowly flows through a refractory channel to the next stage, one that forever changed the entire industry. This is a bath of tin. That's right, glass literally floats on the surface of molten metal. This process is called the float method. Tin is way denser than glass, so the glass mass spreads across it in a perfect mirror-smooth layer. Just look at this pool 160 feet long, filled with liquid tin. Glass comes out of the furnace and settles onto this metal, becoming perfectly flat through simple gravity. No grinding wheels or expensive polishing. Physics does all the work for us. This is where engineers set the thickness of your future window. Pull the glass faster using special rollers, and it becomes as thin as 1/8 of an inch. Slow it down, and you can get a solid panel a full inch thick that's not so easy to damage. Temperature here gradually drops to 1100 degrees Fahrenheit, and the glass starts to harden, transforming from fiery liquid into an endless ribbon. Next, this ribbon enters an annealing tunnel that engineers call a layer. This is where a critically important process happens. If the glass cools too quickly, internal stresses build up, and it'll literally explode from the slightest touch once it hits the warehouse. So we slowly drop the temperature over several hundred feet of travel. This demands incredible precision, because every single degree matters for the molecular structure. The glass rolls on special steel rollers that have to be perfectly smooth, so they won't leave a single microscopic scratch on the surface, which hasn't fully solidified yet and remains vulnerable. When the glass finally cools down, lasers start checking it. It's basically digital quality control, where machines hunt for microscopic air bubbles or tiny dust particles that might have snuck into the mix back in the furnace. If the system spots even the tiniest flaw, it instantly marks that spot with special paint, and automated cutters just remove the damaged section, sending it back for remelting. The cutters themselves work at incredible speeds. Sharp diamond rollers score perfect lines. Then mechanical arms confidently snap off sheets in the exact sizes needed. But this is just regular glass, the stuff you see in old buildings. We came here for the super strong material that holds up the weight of a skyscraper. To turn glass into a true iron warrior, you've got to temper it. This is my favorite stage, because it's like putting glass through brutal boot camp. A sheet of glass gets heated again to 1200 degrees Fahrenheit, then suddenly blasted with powerful jets of cold air from both sides. This thermal shock creates massive pressure on the glass surface, compressing it, while the center stays in a tensile state. This makes the glass 5 times stronger than regular glass. If you try to hit this stuff with a heavy hammer, it might just bounce right back into your forehead. And here's the best part. When this glass finally does break under incredible pressure, it doesn't shatter into sharp daggers that can slice you up. Instead, it crumbles into thousands of tiny blunt pieces. It's a global safety standard that allows us to use it in modern cars, sports arenas, and massive shopping malls. But if we're talking about skyscrapers in cities that get hurricanes, tempering alone won't cut it. That's when we use lamination. We take 2 separate sheets of glass and glue them together using a special film made of transparent polymer. This technological sandwich gets sent to an autoclave, a massive oven under pressure, where all the air gets sucked out and the film becomes completely transparent, bonding the sheets together at the molecular level. If a brick or even something heavier hits that glass, it'll spiderweb with cracks but stay hanging on that film, without creating a hole all the way through. This is the exact glass that protects people in banks or on observation decks 1,000 feet above the ground. You're standing on a transparent floor, on the 100th story, and you know for certain that polymer layer will hold the weight of 10 people without breaking a sweat. At the end of the line, we see finished steel giants being loaded onto specialized trucks. One of these sheets can weigh over 3,000 pounds, which is why people stopped using their own hands to move them a long time ago. Instead, there are powerful vacuum suction cups on cranes that grip the glass with a death grip. It's a spectacle that makes your heart beat faster. A massive, seemingly fragile panel gliding smoothly through the air, destined to become part of a new architectural structure in just a few days. The entire journey from a pile of sand to this moment took only a few hours of intense work. But packed into those hours are decades of complex scientific research and billions of dollars of investment in technology. When you see skyscrapers glistening in the sun, remember, this isn't just architecture. This is frozen fire. Molten metal and sand that went through temperatures of 5,000 degrees Fahrenheit to become transparent. Glass panels withstand wind pressure of hundreds of pounds per square foot. They don't fear snow, hail, or scorching sun. This is the material of the future, getting stronger and smarter every single year. Maybe soon we'll be building entire cities from it. Cities that are completely transparent, yet tougher than the concrete boxes of the last century. Every year, over 80,000 wind turbines are installed worldwide. But few people know that each one hides a true engineering masterpiece inside. A blade over 300 feet long that can withstand hurricane-force winds and operate for decades. How do you create a structure so light it can be lifted by a crane, yet so strong it won't break even at rotational speeds exceeding 180 miles per hour? From glass and carbon fiber to vacuum resin infusion, the process of manufacturing wind turbine blades resembles precision surgery on a spacecraft scale. Stick around till the end, and you'll discover why these giant wings have become the symbol of a new energy revolution. Modern megawatt-class turbine blades range from 196 feet to 262 feet in length, and for offshore projects can exceed 360 feet. Why such size? A wind generator's power output is directly proportional to the square of blade length. A longer blade captures a larger wind area, increasing efficiency and, consequently, project profitability. However, with increasing size comes a cubic increase in mass. If you simply scale up a blade, its weight becomes unacceptable and gravitational and inertial loads become destructive. So the key challenge is maintaining low weight with colossal strength. To solve the weight problem, American manufacturers have almost completely abandoned traditional metals in favor of advanced composite materials. Fiberglass is the primary material. It's relatively cheap, strong, has excellent fatigue resistance, and provides necessary stiffness. Fiberglass cloth forms the outer shell and most of the internal structure. For the longest and most powerful blades, carbon fiber is indispensable. It's twice as light and several times stronger than fiberglass. It's strategically used in the most heavily loaded zones, in the longitudinal beams called spar caps that run the entire length of the blade and are responsible for its structural integrity. The fibers are impregnated with epoxy or polyester resins, which, when cured, bind the fibers into a single, extremely strong monolith. This is the heart of the process. To create sandwich structures that give the blade volume and stiffness at minimum weight, analogous to honeycombs, lightweight core materials are used, such as balsa wood or specialized polymer foams. Manufacturing a blade is a multi-month process that requires surgical precision, even though it takes place in massive facilities. The first step is creating a giant mold, or matrix. This typically consists of two massive halves made of durable composites or steel. The mold must perfectly replicate the complex aerodynamic profile of the future blade. Profile accuracy is critical for aerodynamic efficiency and noise minimization. Spar caps are essentially the blade's spine. At this stage, strips of carbon fiber or fiberglass are laid down. If the blade is very large, this process is often fully automated. Robotic systems precisely lay fiber layers into special grooves in the mold. This part is the thickest and bears the main bending loads. The next step is laying fiberglass layers that form the blade's outer shell, as well as core material blocks. Fibers are typically laid by hand by experienced technicians, or using automated fiber placement to ensure proper fiber orientation that will resist predicted loads. After laying all the dry layers, the mold is closed and a deep vacuum is created inside. Resin, epoxy, or polyester is introduced into the mold, and vacuum pressure uniformly and completely impregnates all the fibers, displacing air and ensuring maximum density and strength. This process allows manufacturing large, nearly void-free structures with precisely controlled fiber-to-resin ratios. The resin-filled blade is placed in special ovens or left in the mold under climate-controlled conditions. Heat initiates the polymerization process, during which liquid resin transforms into a solid, strong polymer. This process is lengthy and requires constant temperature control along the entire blade length to avoid internal stresses. After curing, the blades are removed from the mold. The two blade halves, upper and lower, are joined together using special adhesive and additional composite layers. This is one of the most complex stages as it requires perfect alignment over dozens of feet. The root section is where the blade attaches to the turbine nacelle. Powerful steel or composite bushings are embedded here that will withstand enormous loads during rotation and transmit torque. After assembly, the blade is sanded and then coated with special protective coatings. These coatings, particularly on the leading edge, are vital for protecting composite material from erosion caused by rain, hail, dust, and insects, which act like sandblasting at high blade tip speeds. American manufacturers like GE Renewable Energy and TPI Composites pay special attention to quality and innovation to guarantee blade reliability for 20 or even 25 years of operation. No blade leaves the factory without thorough inspection. Since internal defects like air pockets or poor resin impregnation can lead to catastrophic failure. Ultrasonic scanning detects internal defects, voids, and composite delamination. Thermography measures thermal signatures to identify areas with varying density, such as defective bonding. Each new blade model undergoes extreme testing in specialized laboratories. The blade is bent to its strength limit, simulating the strongest wind loads and loads from its own weight to ensure it won't break. Then the blade is forcibly bent forward and backward, up and down millions of times, simulating decades of operation to test material fatigue resistance. After manufacturing comes another engineering challenge: logistics. Transporting a blade over 260 feet from the factory, often located in interior U.S. states, to the installation site requires special low-bed semi-trailers that can rotate the blade around corners and lift it to avoid collisions with infrastructure. It's a unique logistical dance that often requires temporary road closures. Transporting blades is a logistical nightmare. Blade length can easily exceed the wingspan of a Boeing 747. To transport such structures on U.S. roads, special extended semi-trailers are used that can lift, rotate, and tilt the blade at intersections and in mountains. This requires temporary road closures, removal of road signs, and even traffic lights. The U.S. continues investing in developing even longer, lighter, and stronger blades, researching thermoplastic materials for better recyclability, and segmented designs to simplify logistics. This ensures that the engineering marvel born in factories will remain a key element in achieving energy security and sustainability. Some blades, especially older ones that have already served their term, instead of being recycled, are buried in specialized landfills in sparsely populated states like Wyoming. Due to their volume and composite material, fiberglass that doesn't decompose, they can occupy significant areas, becoming museums of green energy. The tips of the longest blades can reach rotational speeds of 180 miles per hour. Though they don't exceed the speed of sound, this requires the blade tip to be perfectly designed and protected from erosion. An ordinary raindrop hitting the blade at such speed has destructive force similar to sandblasting. This forces manufacturers to develop high-tech but expensive protective coatings for blade leading edges. Engineers in the US are developing smart blades that can change their shape or have segmented tips. This allows the turbine to adapt to changing wind speeds and thus increase efficiency and reduce loads. Every year, machines are built around the world so massive and powerful that a single one could supply electricity to an entire city and costs as much as dozens of private jets. But what if I told you that inside this colossal structure, there are parts machined with precision, thinner than a human hair, and that one tiny mistake could cost millions of dollars or even destroy everything. Today we're going inside a place almost no one gets to see, the heart of turbine manufacturing. And trust me, what you're about to see will completely change how you think about engineering, if you stick around till the end. Let's start with the fact that there are two main types of these turbines, and they work on very different principles. First, the steam turbine. You'll find these at nuclear and thermal power plants, on massive tankers and icebreakers. Second, the gas turbine. It's more like a giant jet engine without wings and lives mostly at gas-fired power plants and on some military vessels. Here at the factory they make both types, but we're heading first to the steam ones because they're older, more massive, and look like they were invented 2 centuries ago. Which, actually, they were, but they're still very much around. How a steam turbine works: short and formula-free. There's a boiler that heats water into pressurized steam at anywhere from 800 to 3,000 pounds per square inch. This steam, hot, pressurized, angry, blasts through nozzles onto rotor blades. The blades start spinning. The rotor spins the shaft. The shaft spins a generator or a ship's propeller. The steam cools down, condenses back into water, and returns to the boiler. The cycle is closed. Sounds simple, but for this simple not to explode into pieces and to run for 3 years without major repairs, you need all of this around me. The first shop they take me to is the foundry. This is where every turbine begins. The casing, the outer shell that holds all the internal components under pressure, is cast from alloy steel or cast iron, depending on operating parameters. For steam turbines in large power plants, the casing is cast in 2 or 3 tiers, and each tier is a separate mold. The mass of 1/2 of a casing can reach 60 to 80 tons. The metal is melted in arc furnaces with a capacity of 50 to 150 tons of molten metal, and the temperature there is around 5,000 degrees Fahrenheit. The mold for a large casing is a pit in the floor, 6 to 10 feet deep, lined with refractory clay. The metal is poured through a system of channels, and the entire process of filling one large mold takes 15 to 30 minutes. Then the casting cools, naturally from several days to 2 weeks, depending on the mass. After cooling, the casting goes to its first inspection. Ultrasonic testing searches for voids and inclusions inside, spots where the metal didn't fuse the way it should. X-rays check critical zones. If they find something significant, the casting goes back to remelt. No compromises. The rejection rate at this stage runs 3 to 8% depending on the casting's complexity, and that's completely normal for parts this size. Next, machining. Now, here in the shop floor, there are machines that made my jaw drop. The horizontal boring mill that machines the inner casing surface. It's about 60 feet long. The table where the part sits moves. The spindle stays put. The tool freely bores the bearing and seal mounting surfaces to an accuracy of plus or minus 0.5 of an inch. Why so precise? Because the rotor spinning inside at 1500 to 3600 revolutions per minute has a clearance between its blades and the casing of 50 to 150 microinches. 1% efficiency loss at a large power plant. That's millions of dollars in extra fuel costs per year. The rotor is the star of this story. It's a shaft carrying discs with blades, and it's the most complex part of the entire turbine. The shaft for a large steam turbine is a forging made from special chromium molybdenum vanadium steel, 20 to 40 feet long and weighing 20 to 60 tons in its rough state. A forging means you take a red-hot ingot of metal and just hammer it with a press weighing 5,000 to 50,000 tons to give it the shape you need. The grain structure of the metal during forging gets oriented along the shaft's axis. That's how you achieve torsional strength. After forging, the shaft goes through heat treatment again, then heads to the machine shop. Turning takes 2 to 4 weeks of continuous work on a lathe that's nearly 70 feet long. Chips fly, coolant flows, and machining away from that massive blank reveals the sleek shaft you saw in the drawings. This is the part where I'm always amazed. A gigantic component, yet precision like a watch mechanism. Blades are a separate production line. Steam turbines at large power plants have anywhere from 8 to 20 stages, and each stage is a disc with blades. First stage blades are small, sometimes less than 2 inches tall, because the steam there is still under high pressure and dense. Last stage blades are massive, up to 5 or 6 feet long on the largest turbines. These blades are forged and milled from iron-based alloys or stainless steel, and in their final profile, they have an aerodynamic shape with precision to within plus or minus 0.002 of an inch along the entire length. Each blade is checked for resonant frequency. It can't match the operating rotational frequency of the rotor, or else after a few thousand hours, a fatigue crack will develop from vibration. How they test this is simple. They tap the blade with a small hammer and listen with a special acoustic sensor. A very elegant method for such a serious problem. Assembling the rotor. This is when it starts to feel like an operating room. Bladed discs get mounted onto the shaft using shrink fitting. The disc gets heated to 300 to 400 degrees Fahrenheit. It expands, slides onto the shaft, then cools and grips the shaft with a force no bolt could ever match. No threads, no glue, just temperature difference and precision sizing. The interference fit when cold, 1 to 3/1000 of an inch per inch of diameter. After assembly, the rotor gets balanced, and this takes 1 to 3 days. Balancing happens on a specialized rig, where the shaft spins on bearings while sensors register vibration. If there's any imbalance, metal gets removed from certain spots, or balancing inserts get installed. Allowable residual vibration on a large rotor, fractions of an ounce per inch of radius. If you think that's strict, you're thinking right. After assembly, the turbine heads to the test stand. At full operating parameters, pressure and temperature, they run the turbine for 24 to 72 hours. Sensors track bearing temperatures, vibration, steam leaks, power output. If anything goes outside the limits, stop, disassemble, analyze. There have been cases where they found a defect here that the X-ray missed initially. So the test stand isn't just a formality. It's the last line of defense before shipping. The finished turbine gets broken down into transport blocks, casing separate, rotor separate, auxiliary equipment separate. A large turbine rotor travels on a special trailer with hydraulic suspension, the kind you've seen on YouTube, with 18 axles moving at 20 miles per year. They coordinate the route a month in advance. Every bridge height and every turn width needs checking from the factory to the port or customer. Sometimes for one of these transports, they temporarily remove road signs and even take down power lines over the highway. I asked the chief engineer how many turbines they build per year. He said 12 to 20 of various types. That's it. Less than 2 per month. But each one runs for 30 to 50 years and generates electricity for hundreds of thousands of people every day. Some things don't need high-volume production. Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents. A modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it, a giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about 1/4 pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation: drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Genan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian Tunnels. Toronto TTC North Subway Extension, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, it's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, Worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site: concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools. Right here, in the depths of the concrete wall, the energy that drives the modern world is born. When all main structures are completed, foundation, dam wall, turbines, and generators, comes the moment of returning the river to its new channel. Engineers block the bypass canal, and water again gets directed toward the dam, but now in a controlled manner. It begins gradually filling the reservoir that formed behind the concrete wall. This process isn't quick. To avoid sudden level changes that could damage the structure or cause landslides, filling happens in stages. Sometimes this takes weeks or even months. Meanwhile, they monitor bank conditions, water levels, wall pressure, and turbine operation. When the reservoir reaches optimal level, the hydroelectric plant enters normal operation. It starts steadily producing electricity that enters the grid. To build one dam, they use enough material to construct 10 modern skyscrapers. This isn't an exaggeration. Concrete gets poured in layers, day and night, thousands of tons at a time. It's delivered by conveyors, mixers, barges, sometimes even cable cars. Such volume is needed to create a monolithic wall capable of restraining a river. But concrete is only part of the story. Water held back by the dam exerts colossal pressure. On every square foot of wall, dozens of tons of force. It's like several trucks pressing simultaneously on a door-sized area. Such pressure doesn't just affect the structure, but also creates potential for energy production. The greater the water drop height, the more energy can be obtained. Water flow gets directed through turbines that spin and drive generators. All this without burning fuel, without emissions, just nature's force. One large hydroelectric plant can provide electricity to millions of people. That's schools, hospitals, factories, neighborhoods, entire cities. In some countries, hydropower is the main electricity source, stable and ecological. When they build a dam, the river stops flowing freely. It gets restrained, redirected, accumulated. This changes the landscape. Valleys, forests, fields get flooded. Dozens of square miles of territory where people once lived, trees grew, and animals ran can end up underwater. Sometimes entire villages need relocation. Roads, bridges, and cemeteries need moving. It's a painful process requiring social support, compensation, and careful planning. At the same time, the river's life changes. Water flow becomes controlled, affecting fish accustomed to seasonal migrations. For example, salmon or sturgeon can lose access to spawning grounds if special fish passages aren't provided. Channels or ladders that fish can use to bypass the dam. Without them, populations decrease and sometimes disappear completely. Water's chemical composition also changes, along with its temperature and oxygen levels. In reservoirs, water stagnates, which can cause algae blooms or death of some species. The region's microclimate changes. It becomes more humid, fog appears, wind patterns shift. That's why modern projects try to minimize ecological damage. Engineers work together with ecologists, hydrobiologists, and geographers. They create fish passages, plant new forests, relocate rare species, and form artificial islands for birds. In some cases, they even create new ecosystems, wetlands and floodplains that compensate for losses. A hydroelectric plant is a powerful source of clean energy, but it shouldn't be a source of destruction. Balance between technical progress and nature is the main challenge of the 21st century. And this is where new construction ethics are born, not just to build, but to preserve. So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight-up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2,700 to 2,900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade, including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about a quarter of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees Celsius flows through and keeps the metal in the working zone. These channels are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic. And it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it, following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees, because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, and we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material, then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic. although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and zero defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every year, millions of tons of metal waste get recycled worldwide, but only at the very end of this massive process does a substance emerge that's heavier than almost anything you've ever held in your hands. Picture a metal where a tiny piece weighs as much as a brick, and extracting it is more like hunting ghosts through fire and acid. Today, we're stepping inside a facility where one of the rarest and most mysterious metals on the planet is born from dirty sludge: osmium. But the most shocking part isn't its weight. It's what you have to go through to get even one small bar. And trust me, if you stick around until the end of this video, you'll learn a fact about this metal that literally breaks logic and makes you question the laws of physics. We're now entering the primary processing facility for platinum sludges. Everything around here is humming, steam's bursting out from under valves, and the workers look like they're gearing up for a flight to another galaxy based on the sheer amount of protective gear they're wearing. And that's no surprise. Osmium is basically the heavyweight champion of the periodic table, and it doesn't tolerate amateurs. It's twice as dense as lead. Just think about that for a second. If you grab a cube of this metal with sides only 4 inches long, it'll weigh nearly 22 pounds. That's like trying to pick up a full-grown cat that's compressed itself down to the size of a matchbox. The process of extracting osmium is a real adventure for anyone who loves complex flowcharts and intellectual challenges. This metal doesn't just lie around in proud nuggets deep in the earth, waiting for some lucky prospector to pick it up and slip it into their pocket. Nope, it's way trickier than that, and hides itself in the residues left over from the industrial purification of copper and nickel. Picture a whole mountain of rock that's already been processed, squeezed for everything possible, and only at the very end, in the dirty sludge, this heavyweight remains. You and I walk past massive vats where all hell breaks loose because the metal mixture gets hit with aggressive chlorine and insanely high temperatures. It looks like a set from a movie about the future, where humanity learned to extract value from dust. The work starts with anode slime. That's the sediment left over after electrolysis. To get to the osmium, specialists have to literally dismantle the molecular structure of this waste. First, the slime gets treated with acids to wash out the more cooperative metals. When it's our hero's turn, thermal processing kicks in. Temperatures here reach thousands of degrees Fahrenheit. This isn't just heating, it's total transformation of matter under the watch of dozens of sensors. When the mixture hits the reactors with chlorine, the most critical stage begins. Osmium reacts and transforms into a volatile compound. This gas needs to be captured with pharmaceutical precision. The slightest error in pressure or temperature, and the precious metal simply flies up the stack, leaving behind nothing but a foul smell. Special absorption towers step by step pull the gas in, converting it into a solution. It's like hunting a ghost, except instead of traps, you're using complex chemical filters. Next, the solution goes through several more purification stages until finally a precipitate appears: pure osmium salt. But that's still not the end of the road. This salt gets roasted again in a stream of hydrogen to produce that same dark blue powder. Every pound of this powder, that's the result of hundreds of workers and massive machines grinding away. Looking at these vats, you realize that osmium extraction isn't just metallurgy. It's the pinnacle of engineering genius, where every move costs thousands of dollars. This is work for the patient and the bold, because this metal doesn't forgive mistakes, but it rewards those who make it through all these fiery and chemical obstacles with its otherworldly strength. To extract it, you need to convert it into osmium tetroxide. And this is where the fun really begins, because this gas smells like someone decided to mix bleach with rotten radish and set it all on fire in a closed room. The metal's name actually comes from the Greek word meaning smell, and trust me, the Greeks knew what they were talking about. We move on to the separation laboratory. Here reigns an atmosphere of sterility that contrasts with the dirty rumble of the previous workshop. Scientists in white coats manipulate glass tubes and retorts. The whole process looks like a very expensive and dangerous cooking show. They extract osmium as a fine, dark blue powder. This powder looks beautiful, but it's incredibly treacherous. If you heat it in open air, it instantly becomes a toxic gas that can ruin not just your day, but your health for years to come. So airtightness is everything here. Look at these furnaces. They operate at temperatures that are hard to fathom. over 5,000 degrees Fahrenheit. That's way hotter than the surface of some stars. Because osmium has an incredibly high melting point, you can't just melt it in a bucket and pour it into molds. They use powder metallurgy methods here. The powder gets pressed under gigantic pressure, then sintered in a vacuum. What you get is like a metal sandwich that then becomes a monolith. It's fascinating to watch them try to cut this metal. Regular saws and drills are useless here. They just dull or snap like they're made of chocolate. Osmium is so hard and brittle at the same time that you can only work with it using lasers or supersonic water jets with added abrasives. It's a real challenge for engineers. Every disc or sphere produced costs a small fortune, because making a single part burns as much energy as a small town uses over a weekend. Why even bother with such a finicky material, you might ask? Well, besides looking like a chunk of frozen blue sky, it's incredibly wear resistant. It's used where you need something eternal, in high voltage switch contacts or in the tips of very expensive fountain pens used to sign peace treaties. This is one of those cases where quality justifies every cent spent and every whiff of that weird smell of ozone and chemistry. I'm standing next to a finished ingot. It's small, about the size of my palm, but when I try to move it, my muscles tense up like I'm pushing a small car. This little guy weighs about 35 pounds. You can't capture this feeling through a camera. It violates every law of logic we're used to in everyday life. You expect lightness, and you get a gravitational punch to your arms. Now we're moving into the packaging zone. Even here, everything's serious. Every gram is accounted for. Every ingot has its own certificate and number. This isn't the kind of metal you accidentally forget in your work jacket pocket. Its market price swings so wildly that investors sometimes drink more sedatives than coffee. But demand for this blue shimmer keeps growing because the world's getting more technological, and osmium, it's exactly the ingredient that makes modern electronics reliable. You know what struck me most at this plant? It's the people. They talk about this metal like it's a living creature with a really bad temper, one they've learned to respect and tame just a little. There's no room for rushing here. Every move is calculated to the inch. Every second in the furnace is accounted for. This isn't just manufacturing. It's a battle of human intellect against the physical limits of matter. We're wrapping up our tour at the finished product display. Here you'll find small parts that'll soon ship all over the world. Some will end up in spacecraft, others will become part of medical devices. And every time you hear about something incredibly strong and durable, remember this blue, smelly, and impossibly heavy metal. Hope you enjoyed this walk along the edge of the periodic table. It was tough in every sense of the word. Don't forget, the world around us is way more interesting than it seems at first glance, especially if you peek behind the fence of a big factory. It was fun showing you this metallic extreme. Until next time at new facilities, where we'll definitely find something else that'll make your eyebrows shoot straight up in surprise. Did you enjoy this format? Maybe you'd like me to prepare a detailed script about manufacturing another rare metal, or talk about the logistics of moving these heavy ingots around. You can find in ordinary dirt that contains so much energy, 2 pounds replaces 6 million pounds of coal. A rock you shouldn't touch with bare hands, controlled more strictly than gold, and determines whether entire cities have power in winter. This is uranium ore, the planet's most controversial geological resource, simultaneously saving us from climate catastrophe and threatening nuclear apocalypse. Let's dive into a world where geology collides with nuclear physics, and ordinary stone can change the fate of civilization. Let's start with what uranium ore actually looks like. If you're picturing something bright green, glowing in the dark like those mutant movies, I hate to break it to you. Most uranium ore looks like regular gray or yellowish brown rock, sometimes with a greenish tint, sometimes with black spots, but nothing particularly mind-blowing. You could walk right past this stuff in the mountains and never even know it's radioactive. True, there are minerals like uraninite or torbanite that have a brighter yellow-green color, but that's more the exception. Real glow happens but not from the uranium itself. Some uranium minerals fluoresce under ultraviolet light. They light up bright green or yellow. Geologists use this to find deposits. They shine UV lamps in the dark, and the ore gives itself away with that glow. Looks straight up cosmic, especially in caves, where the walls suddenly burst into neon colors. But the main feature of uranium ore isn't its appearance, it's what's inside. Uranium-238 and uranium-235 are isotopes that slowly decay, releasing radioactive radiation for billions of years now. 1 gram of uranium emits around 12,000 radioactive particles per second. Not enough to kill you instantly, but enough to build up a dangerous dose over years if you constantly carried a rock like that in your pocket. Uranium is found everywhere, in rocks, soil, water, even seawater. The average concentration in Earth's crust is about 3 parts per million. That means in every ton of ordinary dirt, there's roughly 3 grams of uranium. But for industrial mining, you need concentrations at least 100 times higher, from 0.3% and up. Deposits like that are rare and only form under specific geological conditions. The richest deposits are found in Kazakhstan, Canada, Australia, Niger, and Namibia. Kazakhstan leads in production, about 45% of global output. Canadian deposits in the Athabasca Basin contain ore with uranium concentrations up to 20%. That's fantastically high. For comparison, most deposits have between 0.1 and 1%. How do you mine uranium ore? There are 2 main methods: traditional shaft mining and in-situ leaching, which sounds like something from a sci-fi movie but actually works. In the first case, you dig a mine or an open pit, blast the rock with explosives, load it onto dump trucks, and haul it to a processing plant. Just like any other ore, except with radiation. Miners work under special conditions: constant radiation monitoring, dosimeters on every worker, limited time in high radiation zones. The air in the mines can contain radon, a radioactive gas released when uranium decays. It's constantly pumped out by powerful ventilation systems. Without this, miners would receive dangerous radiation doses in a matter of months. Now, about in-situ leaching. Instead of digging a mine, they drill boreholes straight down to the ore deposit at depths of 300 or 600 feet. Through some boreholes, they pump in a solution, usually sulfuric acid with an oxidizer, or soda solution, depending on the type of ore. This solution dissolves the uranium right there underground. Through other boreholes, they pump out the solution that now contains dissolved uranium. At the surface, they extract the uranium from this solution using chemical methods. Underground leaching is cheaper, safer for miners, and less destructive to the environment. You don't have to haul millions of tons of rock to the surface. That's how most uranium is extracted in Kazakhstan. But the method only works for certain types of deposits where the ore sits in porous sandstone that a solution can filter through. After extraction, the ore needs processing. It's crushed, ground up, and also treated with acid or alkali to dissolve the uranium. What you get is a solution containing uranium, along with a bunch of other elements: iron, calcium, sulfur, rare earth elements. This solution is purified, and the uranium is precipitated as a concentrate called yellow cake. Though it's not always actually yellow, it can be greenish, brown, or black depending on the impurities. Yellow cake. That's uranium oxide with a concentration of about 80% uranium. Looks like a powder or a sintered mass. This is already a concentrated product that gets shipped to the next stage of processing. But it's still natural uranium, a mix of isotopes, where uranium-238 makes up 99.2% and uranium-235 only 0.7%. And for nuclear fuel in most reactors, you need to enrich uranium-235 up to 3 to 5%. Uranium enrichment. That's a separate high-tech industry, wrapped in secrecy and international controls. First, yellow cake gets converted into gas. It's the only uranium compound that easily transitions to a gaseous state under normal conditions. though normal conditions here means a temperature around 140 degrees Fahrenheit with a slight increase in pressure. Then, this gas is run through thousands of cascades of centrifuges or gas diffusion plants. The centrifuges spin at around 100,000 revolutions per minute, so fast that the outer edge moves at nearly the speed of sound. At this rotation speed, heavier molecules containing uranium-238 concentrate slightly more near the walls, while lighter ones with uranium-235 stay closer to the center. The difference is tiny, which is why thousands of sequential stages are needed. The entire enrichment process takes months and consumes enormous amounts of electricity. A single enrichment facility can use as much power as a medium-sized city. That's why these plants are built next to major power stations or in countries with cheap electricity. And this is where geopolitics comes in. Those same centrifuges can be used to enrich uranium, not to 5% for power plants, but to 90% and beyond for nuclear weapons. That's why the international community tightly controls who gets access to these technologies. The Atomic Energy Agency conducts inspections, verifies that countries are following agreements and not building weapons under the guise of peaceful energy. Enriched uranium gets converted back into solid form, uranium dioxide. From it, they press small cylindrical pellets roughly half an inch in diameter and about 2/3 of an inch long. These tiny pellets contain as much energy as half a ton of coal, or around 130 gallons of oil. Hundreds of these pellets get loaded into long metal tubes made of zirconium alloy, fuel rods, and hundreds of rods form a fuel assembly for the reactor. A single modern nuclear reactor, 1 gigawatt of power, holds about 100 tons of uranium fuel. That's enough for 3 to 4 years of operation. During that time, the reactor generates enough electricity to power a city of 1 million people for those entire years, all from 100 tons of uranium. By comparison, a coal plant with the same output burns through roughly 10 million tons of coal over that same period. But there's a dark side. Spent nuclear fuel is the most dangerous waste humanity has ever created. After 3 to 4 years inside a reactor, the fuel becomes saturated with fission products, radioactive isotopes like cesium-137, strontium-90, iodine-131, and many others. Some of them stay radioactive for thousands of years. A single fuel assembly radiates so much that it can kill a person in minutes from just a few feet away. Spent fuel is first stored in water pools right at the plant. The water cools it and shields the radiation. After a few years, once the most active isotopes have decayed a bit, the fuel can be moved to dry storage, thick-walled containers made of concrete and steel. These containers need to last hundreds of thousands of years, until radioactivity drops to safe levels. Where and how to store them that long? A question humanity still doesn't have a good answer to. Some countries reprocess spent fuel, extracting unburned uranium and newly created plutonium, which can be used again. France, the UK, Japan have such facilities. But reprocessing is expensive, complex, and creates additional risks of nuclear materials spreading. The US decided not to reprocess and to simply store spent fuel, waiting for a solution to the problem in the future. Control over the uranium fuel cycle, from mining to disposal, is a matter of national security. Countries with a complete cycle gain energy independence, but also the potential ability to build weapons. That's why the spread of these technologies is tightly controlled by international treaties. The Nuclear Non-Proliferation Treaty recognizes 5 nuclear weapon states and prohibits others from developing nuclear weapons, though it allows peaceful use of atomic energy. But reality is more complicated. India, Pakistan, North Korea built nuclear weapons without signing the treaty or by violating it. Iran is developing a uranium enrichment program, claiming it's for energy, but raising Western suspicions. Israel has nuclear weapons, though it doesn't officially acknowledge it. Uranium ore and the technologies to process it have become tools of global politics. Uranium mining also has environmental consequences. Tailings ponds, Massive waste piles left after uranium extraction contain radioactive elements, heavy metals, and chemical residues. If improperly contained, they contaminate groundwater for decades. There are stories of towns abandoned due to radiation pollution from uranium mining. For example, the city of Melusu in Kyrgyzstan is surrounded by millions of tons of radioactive waste from the Soviet era, which still poses a danger today. But there's another side to this. Nuclear power provides roughly 10% of the world's electricity with virtually zero carbon emissions. In France, nuclear plants generate 70% of the country's electricity, giving it one of the lowest per capita carbon footprints among developed nations. In the context of the climate crisis, nuclear energy is viewed as a necessary component of the transition to a low-carbon economy. How much uranium is left on Earth? Identified reserves stand at around 6 million tons, enough for 1 to 200 years at current consumption rates. But that's only what's already been found and is economically viable to extract. Potentially available resources are far greater, including uranium in seawater. There's roughly 4 billion tons of it there, though extraction is still very expensive. In every second of our lives, there are metals we don't even suspect. Without them, there would be no smartphones, electric cars, or even jet aircraft. And now imagine a place where, in the middle of the desert, under the scorching California sun, the United States creates a strategic resource of the future, without a single pound of Chinese raw materials. Here, at Mountain Pass, they mine 43,000 tons of rare earth metals annually. Rocks that look ordinary are transformed into materials for lasers, engines, and defense systems. But there's something almost no one knows about. And if you watch till the end, you'll understand why this dust from the desert can change the world. Today here, in the dust and heat, MP Materials Company mines 43,000 tons of rare earth concentrate per year, all without a single pound of Chinese raw materials. For a country that for decades depended on imports from China, this is a strategic breakthrough. The main star of this place is bastnasite, a mineral that looks like an ordinary stone but contains treasures inside: lanthanum, cerium, neodymium, and praseodymium. These very elements give life to modern magnets, lasers, electric cars, and jet aircraft. Everything begins in the depths of the quarry. Huge excavators and 300-ton trucks carry rock to the crusher. Next comes the flotation process, similar to a magic sieve. Crushed ore is mixed with water and special reagents. All this turns into foam, and bastnasite particles float to the surface, while waste settles to the bottom. After flotation, bastnasite goes for chemical expertise. In MP Materials laboratories, it's transformed into concentrate, and then into individual elements. This is a complex sequence of extractions and washes, where each metal chooses its own path. Once, this stage was performed in China. Now the United States is gradually building a full production cycle, from ore to finished magnets. Thanks to this, the country has already replaced 80% of its former imports from Asia, and this is just the beginning. It sounds like science fiction, but it's a fact. 2 pounds of cerium can become material for optical lenses of laser systems in military equipment. Other elements, like neodymium, are used in powerful magnets of jet engines and in missile guidance systems. All this means that every ton of ore from Mountain Pass isn't just raw material. It's a piece of American defense independence. The California desert isn't just scorched by the sun, it's politically charged. Mountain Pass is a symbol of a new era where technology and geopolitics merge. Today, American engineers, in hard hats and safety glasses, are literally building their own supply chain of the future, step by step displacing the Chinese monopoly. Just as in the 60s, when the United States first launched a satellite, now they're trying to be first to build an independent rare earth elements industry. And it all starts right here, among the sands, where it was once quiet, but now machines rumble, and the fire of smelting furnaces glows. If you gather all the rare earth elements mined here per year, it's 43,000 tons of concentrate. Outwardly ordinary dust, but actually strategic raw material, more valuable than gold. And if this dust were transformed into finished products, it would power more than 100,000 electric vehicles, those that race without a drop of gasoline thanks to neodymium magnets in motors. The same metals would ensure the operation of hundreds of guidance systems for F-35 fighters, where precision depends on microscopic lasers and sensors. And also, tens of thousands of medical lasers used for eye surgeries or to stop bleeding in military hospitals. The irony is that Mountain Pass isn't a megapolis or a Silicon Valley laboratory, but a patch of land in the middle of the desert. But it's precisely this place that's becoming a PowerPoint again. Every kilogram of cerium mined here is a potential lens for lasers in defense systems. Every gram of neodymium is a piece of an engine for an electric car or satellite. It's worth talking separately about cerium. Cerium isn't just another metal on the list of rare earth elements. It's one of those that sits quietly beneath the surface of technologies, but without it, the modern world would look completely different. Imagine a desert quarry, drilling rigs, machine cries, and dust, and among all this, under sand and stone, hides a complex chemical actor that transforms from an ordinary mineral into a material that affects aircraft, phones, and even medicine. In appearance, an ordinary grayish powder, nothing special. But this is a true alchemist among metals. Without it, there would be no clean glass in telescopes, no shine in smartphones, no precision of lasers, and no cleaner air from automobile exhausts. 1 gram of cerium can do what other materials can't even in hundreds of times larger quantities. Cerium is a true master of transformations. In catalysts, it behaves like a chemical chameleon. It intercepts and releases oxygen, converting harmful gases into harmless ones. In glass, it extinguishes ultraviolet light, makes lenses transparent as crystal. Its oxide polishes phone screens, cameras, optical devices, literally erasing microscopic scratches from surfaces to perfect smoothness. Among workers at the plant, there's a joke. Without cerium, the world wouldn't shine. And there's truth in this. Because when it gets into engineers' hands, everything around starts to shine. Literally. It helps see farther, move faster, burn cleaner, heal more precisely. All this, from desert dust, from a place where heat reaches 110 degrees Fahrenheit, and wind sweeps away traces in a few minutes, as a symbol that even in the driest desert, the future can be born. Mountain Pass was once just a point on the map, the only mine of this type in all of North America. But now it's surrounded by an entire network of structures that transform crude ore into pure elements, ready for the most complex technologies, from electric motors to jet guidance systems. MP Materials Company has built here not just a mine, but a closed-cycle production, something America lost back in the 1990s when all supplies depended on China. After many years of research and investments in hundreds of millions of dollars, new lines operate almost without human participation. All processes are controlled by computers. Sensors measure compound purity, robotic cranes move containers, and special cameras capture every dust particle. Air in laboratories is so sterile that it feels like it's not a desert, but a space station. Everything that comes out of these shops is sent to other factories, which are also being built inside the country. In Texas and Ohio, they're building factories that will manufacture permanent magnets, precisely those that ensure the operation of Tesla electric motors, wind turbines, or fighter guidance systems. Once these magnets were supplied from China almost 100%. But now America plans to completely switch to its own materials by 2030. People who work here say they feel part of something bigger than just production. When they watch as a substance comes out of desert soil that will later turn into part of a satellite or a high-precision laser, it resembles a true miracle. Next to the quarry grow warehouses, laboratories, transport hubs, and on the horizon, also solar panels that power this giant. After the mine closed in 2002, when Chinese companies effectively monopolized the rare earth elements market, only a few dozen workers remained in the Mountain Pass area, maintaining security and basic infrastructure. The nearby settlement declined. Stores closed, roads overgrew with weeds, and local families moved out to look for work. When in 2017, MP Materials Company bought out the assets and launched a modernization program, the situation began to change literally from scratch. Over several years, more than 800 jobs were created at the enterprise itself, not counting hundreds of related ones, in transport, chemical supply, technical service, energy, and even local services. In neighboring towns, cafes reopened, schools received funding, and roads, repairs. Besides direct vacancies, MP Materials launched a professional training program, cooperating with local colleges. Graduates of technical specialties can now do internships right at the modern processing plant, where they learn to work with automated lines, flotators, hydrocyclones, and chemical separation systems. Interestingly, jobs here are very diverse, from geologists, chemical engineers, process operators, to programmers and data analysts who control plant operations through digital panels. Each shift means tens of thousands of parameters read by sensors in real time. In a broader sense, the revival of Mountain Pass has become a symbol of the return of American manufacturing, which for decades was exported abroad. Against the background of political statements about reshoring and strengthening the internal supply chain, this project is often cited as proof that even in the desert, you can create a modern, profitable, and stable industry. Every year, over 1,000 giant ships are sent worldwide for scrapping, each weighing up to 50,000 tons and stretching nearly 3 football fields in length. It's like dismantling an entire floating city, with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster is inevitable. But here's the most amazing part. Inside each of these massive vessels hides something that turns scrapping into a real treasure hunt. Workers risk their lives among plasma cutters and toxic fumes to extract these valuables. What exactly are they looking for? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone keeps quiet about? Stay tuned. What you'll learn next will make you look at every ship in port with completely different eyes. Why is ship recycling so important? Vessels that we typically imagine as enormous floating megastructures can be nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for sea travel and cargo transportation. But beyond their massive dimensions, these ships have extremely complex internal structures. Hundreds of feet of cables, pipelines, shafts, and various safety and comfort systems, plus countless different elements and mechanisms that perform different functions. This entire architecture isn't just scrap metal, but a complex organism that must be very carefully and properly dismantled when the ship reaches the end of its service life. It's critically important to properly remove all hazardous substances from the vessel that may have accumulated during its operation. These can be bioactive substances, toxic paints, fuel residues, lubricants, chemicals that, if handled improperly, can contaminate the sea, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a natural disaster. However, scrapping these maritime giants also has a very bright positive side. The metal from which the ship is made is excellent and valuable raw material that can be recycled and returned to production. This metal is used for building houses, machines, construction structures, and also for creating new vessels. This way, it's possible to reduce the need for smelting new steel, save energy and resources, and also reduce the amount of waste. Metal recycling from ships becomes an important link in the closed loop of modern industrial economy. Scrapping such huge objects also makes it possible to free up ports where old ships are standing, so new, modern vessels can take their place. This allows optimizing the work of naval bases and promotes fleet renewal. Additionally, proper recycling helps reduce operational costs for maintaining old ships and improves environmental standards in the maritime industry overall. The ship is delivered to special ship graveyards. These are usually coastlines with shallow water or special slipways. These locations aren't chosen randomly. Shallow water coastlines allow easy approach of the ship to shore, where it can be safely moored and dismantling can begin. Often these are small bays or beaches where the giant vessel is specially brought, so it doesn't interfere with maritime traffic and doesn't damage port infrastructure. Slipways, in turn, are large platforms or special structures where the ship is placed for dismantling on land. They're equipped with everything necessary for convenient and safe work: crane equipment, metal cutting tools, waste removal systems. One of the main tasks for specialists is ensuring environmental safety. After all, during operation, the ship accumulated many substances that, if handled carelessly, can harm the environment. These can be not only lubricants and fuel residues, but also toxic paints or chemicals. Therefore, the entire dismantling process begins with removing all such substances. Fuels and lubricants are drained into special containers and taken away for recycling or disposal to avoid getting into water or soil. Similarly with electronics and furniture, everything that could potentially harm nature is removed as a priority. This stage requires speed and maximum caution so that environmental standards aren't violated. After the ship is cleared of all hazardous and household items, the direct dismantling of the hull begins. And this is the most complex and dangerous part. Using special plasma cutters and gas torches, large steel structures begin to be cut into small pieces. This involves both hand equipment and heavy machinery, cranes, lifts, special manipulators. Plasma cutting allows very precise, fast and efficient metal division that will later go for remelting. The dismantling process itself happens sequentially, stage by stage, starting with the most hard-to-reach or dangerous zones. Metal sheets, beams, decks, and internal partitions are carefully separated so as not to damage structures that might still be needed for analysis or recycling. The complexity is that giant elements are often unevenly distributed and may be under tension, and due to corrosion or hull deformation, some parts can unexpectedly drop or fall at any moment. It's also important to emphasize worker safety. During plasma cutting, hot sparks and toxic fumes arise, requiring special protection from workers, respirators, special clothing, and constant air monitoring. A small mistake or neglect of rules can lead to serious injuries and accidents. Therefore, at every step, the process is regulated by strict safety rules, and the entire site is covered by fire suppression systems and medical support. Dismantling the hull and main steel structures of the ship is, without doubt, an extremely important and complex stage of scrapping a giant vessel. However, after this large body of work is completed, the job doesn't end. Ahead lies another massive phase that requires no less attention and certain skill, as it concerns dismantling and sorting countless smaller, but no less valuable and complex materials. One of the most massive and complex processes is working with cables. The ship contains hundreds of miles of cable networks that provide power and communication between all systems. These are powerful steel cables with insulation made of plastic, rubber, and possibly using non-ferrous metals. Cables don't just remain at the recycling site, they're carefully removed, processed, and sorted. Separating the metal core from insulation materials makes it possible to send pure copper or aluminum for remelting, and the insulation layer for recycling as raw material for new polymers. Workers must act very carefully not to damage long cable pieces, and also observe safety techniques due to the presence of residual substances or rust. Another important category of materials is insulation materials that line or fill the ship's walls, technical rooms, and pipelines. Insulation is often made from special materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After removing insulation, it's sorted and sent to specialized enterprises where these materials can be recycled or disposed of without harming nature. Working with ventilation systems also requires thoroughness. Ventilation pipes and units that were used for air conditioning and circulation in different parts of the ship are dismantled and cleaned of dust, lubricant residues, or other substances. Metal elements of systems typically undergo quality remelting, and plastics or rubber often become raw materials for new products. Special attention is paid to water supply systems and sanitary installations. On board the ship are complex shut-off mechanisms, pipelines, fittings, mixers, tanks, and other equipment. Pipe parts and equipment are carefully separated, cleaned of sediment, lubricants, and other contaminants to be sent for remelting or appropriate recycling. After all, these materials may contain toxic substances, so their disposal or recycling happens strictly according to regulations. No less important is dismantling equipment from the engine room. There are engines, generators, pump systems, turbines, and other complex machinery that typically has significant weight and contains large amounts of metals, including non-ferrous ones. Such equipment is mainly repaired and reused or dismantled into parts, some of which undergo recycling. In individual cases, engines even go for sale as used spare parts, avoiding becoming scrap metal. Furniture, household appliances, lighting, and other interior items of the ship also aren't just thrown away. They're removed and sorted. Wooden, metal, or plastic parts undergo separate recycling or disposal. In some cases, furniture, if it's in good condition, is sold for reuse, and all paints, varnishes, and certain polymer materials are taken for environmental recycling to reduce pollution. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would stop, lights would go dark, and space engines would fall silent. And yet, it's so rare that the entire world fights over every single gram. But here's the real kicker. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that'll flip your understanding of the metal-holding civilization together. Tungsten is a true engineering phenomenon. Its unique properties let us push the boundaries of what's possible in technology, from deep underground to the heights of space. Its story, a story of endurance and unmatched strength. Tungsten is element 74 on the periodic table, one of the transition metals. It has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. To put that in perspective, that's a temperature where most other metals would have vaporized long ago. On top of that, tungsten has the highest tensile strength of any pure metal, at temperatures above 3,000 degrees Fahrenheit. It's incredibly hard and dense, making it irreplaceable for applications demanding maximum resistance to wear, deformation, and extreme temperatures. Tungsten doesn't occur in pure form. It's extracted from ores, with the most common being wolframite and scheelite. Wolframite is a complex compound of iron, manganese, and tungsten, while scheelite is calcium tungstate. These ores, hidden deep in the Earth's crust, are the raw material for all subsequent industrial processing. The world's major tungsten producers include countries like Vietnam, China, Russia, and Canada, which hold significant reserves of this strategic metal. The tungsten extraction process is a complex sequence of mining and metallurgical operations. It starts with exploration and ore extraction from underground mines or open-pit quarries. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep within the earth. It's tough, dangerous work that demands cutting-edge technology and strict safety standards. Thousands of tons of ore are hauled to the surface every single day. After extraction, the ore heads to a processing plant. Here it goes through several stages to separate valuable wolframite or scheelite from other rock. First, the ore gets crushed in crushers and mills until it's a fine powder. Then various enrichment methods kick in: gravity separation, magnetic separation, and flotation. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The concentrate is then processed at metallurgical plants to extract pure tungsten. It's a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent roasting to produce tungsten oxide. The tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. The result is a fine tungsten powder, which forms the foundation for all subsequent products. From this powder, through sintering, tungsten rods, bars, and other blanks are formed. Tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, creating a dense, strong material. One of the most critical applications: manufacturing tungsten carbide. Some seriously tough stuff. These alloys combine tungsten with carbon, plus cobalt or nickel as a binder, creating one of the hardest man-made materials on Earth. They're used to make cutting tools, drill bits, end mills, lathe inserts that can slice through the hardest metals and alloys. Without tungsten carbides, modern manufacturing, metalworking, and oil and gas extraction would grind to a halt. A single pound of tungsten can become a drill bit capable of boring through thousands of feet of rock. Talk about efficiency. Tungsten also sees heavy use in military applications for armor-piercing rounds and bullet cores. Thanks to its extreme density and hardness, tungsten alloys have exceptional penetration characteristics, delivering devastating effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, tungsten is indispensable. It's used to make filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components that need high heat resistance and electrical conductivity. Because of its sky-high melting point, it's used in the aerospace industry for parts exposed to extreme temperatures. High-temperature tungsten alloys are used in jet engines, turbines, and other devices operating under extreme heat. Alloying with tungsten boosts the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with way less toxicity. On top of that, tungsten's used to make ballasts and counterweights in race cars, aircraft, and yachts thanks to its crazy high density. It's even a component in some jewelry because of how hard it is and how resistant to scratches. Tungsten is one of the rarest elements in Earth's crust, which makes mining and producing it especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential resources that haven't been explored yet, the total volume could be significantly higher. That's obviously way less than reserves of metals like iron or aluminum, which really highlights its strategic value. Global tungsten production each year, measured in tons of pure metal, or tungsten oxide equivalent, fluctuates. But in recent years, it's been somewhere between 85,000 and 100,000 metric tons annually. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine this. You could take a worn-out tool that's already served its purpose and transform it back into something brand new, without spending the energy and resources to mine ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is one of the most advanced and efficient processes among all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number. It shows just how valuable this metal is and how much economic sense it makes. Where does used tungsten come from? The main source of secondary raw material for tungsten is, of course, worn-out carbide tools. Those same cutting tools, drill bits, milling cutters made from tungsten carbide. After heavy use, they wear down, lose their edge, or break. Instead of tossing them in the trash, they're collected and sent to recycling plants. Other sources include scrap metal containing tungsten, leftover waste from tungsten product manufacturing, plus some electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of mining ore and initial processing. Recycling dramatically reduces the environmental footprint of tungsten production. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production more green and responsible. Every year around the world, billions of tons of rock are blasted apart with explosives. Tunnels are carved straight through mountains, and rockets are launched into the sky. But few have ever seen the place where the force capable of reshaping landscapes in seconds is born. Today, we gained access to one of the most tightly guarded industrial facilities, where chemistry, fire, and metal come together to create the legendary TNT, the very substance whose explosive power became the world standard. But the scariest and most fascinating part isn't the explosion itself. It's how this yellow powder makes its journey from an ordinary liquid to a material that can obliterate a house-sized boulder. And trust me, if you stick around until the end, you'll learn a fact about TNT production that will completely change how you see modern industry. TNT, or trinitrotoluene as it's also called, showed up way back in the 18th century when chemists started messing around with toluene. Americans call it TNT, short for trinitrotoluene, and to this day, it's the gold standard. 1 gram of TNT, the unit for measuring explosive force. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant stainless steel vessels, where the temperature holds steady at 400 to 480 degrees Fahrenheit. No, seriously, it's hell in there. 200 to 250 degrees Celsius if you convert it. A mixture of nitric and sulfuric acids gets pumped inside. Concentrates so harsh, they'll melt your gloves right off. The nitration process runs anywhere from 3 hours to several days. First you get mononitrotoluene, then dinitrotoluene, and finally trinitro. The acids circulate in a closed loop. They get recycled instead of just dumping them into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything's under control because the slightest shift and the reaction can go sideways. From the reactor, the mixture heads to coolers, long coiled tubes where the hot TNT crystallizes. Then settling tanks. The heavy TNT sinks to the bottom, while the lighter acids get drained off. That jelly-like mass right there, that's raw TNT, still wet with acid. They wash it with hot water at 150 to 180 degrees Fahrenheit to neutralize what's left. The water drains into the sewage system, and the crystals get dried in vacuum ovens, rotating drums that spin like washing machines. Massive stainless steel vats get pumped full of water at temperatures between 150 and 180 degrees Fahrenheit. The water jets out like in an industrial laundry, washing away residual nitric and sulfuric acid. TNT floats in it like jelly in boiling water, spinning, giving up impurities. The process takes half an hour. The water changes 3 times because the first batch is yellow from acid, the second is cloudy, and the third is already clear as a tear. This water doesn't just go down the drain. It gets neutralized with lime in basins, filtered through a 10-foot thick layer of sand, and then released into the river. Ecology stays under control because acid is poison for fish. Meanwhile, the crystals get unloaded. The mass becomes solid, but still 6 to 10% wet. Now comes the drying, the most interesting part. The entrance to this vacuum oven, a room where 20 rotary drums hum, each about 6 feet in diameter. TNT gets shoveled in there, 200 pounds at a time. The drum seals shut, air pumps out until pressure drops to 100 millimeters of mercury, and heating kicks in, 130 to 140 degrees Fahrenheit. Fans blast hot air through the center. The drum spins at 30 rotations per minute, like a washing machine on spin cycle. Crystals tumble, dry evenly, don't stick to the walls. 2 hours, and the doors swing open. Pure yellow powder, temperature 40 degrees, moisture content 0.5%. A worker in a mask pours it into hoppers, where a conveyor will carry it off to granulation. 5 tons per shift from one drum, and no dust because the vacuum pulls everything into filters. The operator jokes, "Dry as my sense of humor." Without this step, TNT would clump together or detonate from moisture. An hour or two, and we've got pure yellow powder. Color? Light yellow to dark orange. Depends on purity. Here we get the top grade, 98% pure product. Next up, granulation. The powder gets moistened, pressed into briquettes the size of a matchbox, then crushed down to granules 2 or 5/1000ths of an inch in diameter. Why granules? Because the powder's easier to pack, doesn't create dust, and detonates evenly. I peer into the press, a giant machine with pistons pushing 200 atmospheres of pressure, and the briquettes come out hard as rock. Then the grinders, hammer mills where the shafts spin at 6,000 revolutions per minute. Dust gets vacuumed out by ventilation, because breathing in TNT, that's gonna cost you. Now packaging. Granules pour into airtight cardboard boxes weighing 100 pounds each. That's the standard for quarries and the military. Every box gets checked for moisture. No more than 0.70%, otherwise the TNT sweats and becomes sensitive. There are also barrel forms for underwater blasts. There the granules get mixed with paraffin so they don't get wet. Boxes are sealed, marked by lot, and done. Off to the warehouse. From here, TNT ships out to quarries, mines, defense. One box is enough to blast through 200 tons of rock. And then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, we're good. Lab techs in masks check purity with a chromatograph. Toluene or acid impurities aren't allowed. Nothing but respect. These people handle explosives like jewelers. Production is massive. 1,000 tons a month, that's millions of pounds. Energy? Electricity from gas turbines, steam from their own boilers. Waste. Acids get regenerated. Toluene gets redistilled. Environment? Filters on a 200-foot smokestack. Wastewater treated until it's clear. Neighbors don't complain. The plant sits 10 miles from the nearest town. Fun fact, TNT doesn't just explode. They melt it at 82 degrees Celsius, 250 Fahrenheit, and pour it into shells like hot wax. Or mix it with gunpowder for plastic charges. In quarries, 1 ton can shatter rock the size of a 3-story building. In mining, you can't punch through a mile-long tunnel without it. And in the military, it's the backbone of torpedoes, mines, bombs. You know how much steel came into this plant? Thousands of tons. Reactors made of chrome molybdenum steel, because regular steel just gets eaten alive by acids. I'm standing in the granulation shop right now. Hear that press rumbling? See those granules pouring into bins like golden sand? The air's clean, but it smells like nitrocellulose. Familiar scent if you've ever been to a powder plant. The operator laughs. Don't breathe too deep, or you'll detonate yourself. Joking, obviously. But the discipline? Ironclad. 8-hour shifts. Lunch break with the clatter of spoons on metal trays. Compare that to the old plants. Back then, everything by hand. Women in skirts packing TNT with bare hands. Explosions once a month. Now, robotic arms, sensors, cameras. Evolution. One worker monitors 10 processes from a control panel. And the pay? Competitive. The plant's like a living organism, roaring, churning, producing power. TNT isn't evil, it's a tool. Builds roads, digs mines, defends the country. Without it, no 1,000-foot bridges, no tunnels under mountains. Can metal burn brighter than the sun? Sounds impossible. But one element does this every day, and we're about to touch its mystery right now. Imagine a material lighter than plastic, yet capable of withstanding loads that break steel. A material hidden in seawater, in stone, in the technology around us, but the way it's extracted looks more like alchemy than industry. And here's the thing. By the end of this video, you'll learn about a property of magnesium that even many engineers have never heard of. Ready to discover what giant furnaces, seawater, and 1,000-degree flames have been hiding? Magnesium is often called the metal that defies intuition. It's lighter than many types of plastic, weighing approximately 0.063 pounds per cubic inch, 1.5 times lighter than aluminum, and nearly 4 times lighter than steel. In your hands, it feels almost hollow inside, yet this metal demonstrates remarkable strength in alloys and can withstand loads its mass simply doesn't suggest. What's most striking is how it burns. Given sufficient temperature, magnesium produces light so intense that its brightness reaches close to 3,500 degrees Fahrenheit, and watching the flame without protection is impossible. That's precisely why magnesium flashes were once used in photography and pyrotechnics. During combustion, it forms white smoke of magnesium oxide, and the flame itself looks as if someone turned on a concentrated beam of sunlight. In nature, pure magnesium doesn't exist. It's bound up in minerals, and the two main sources are dolomite and seawater. Global estimates suggest that the oceans contain over 1.3 quadrillion tons of magnesium, making it one of the most abundant metals in a form accessible to humanity. However, extracting it from water is a complex and energy-intensive process. Picture an industrial facility on the coast where the sea is essentially raw material. Everything runs continuously through a system of powerful pumps. Pipelines stretch from the shore to the processing units, moving thousands of gallons per hour. The water flows into large open or enclosed basins resembling giant reservoirs, where it's filtered for the first time to remove debris, sand, and biological contaminants. After that, in similar tanks, a calcium hydroxide slurry is added. This happens through automated dispensers that feed the material into the water, so the reaction proceeds evenly. From the outside, it looks like a slow transformation of transparent seawater into a cloudy liquid, as if someone added fine white powder that gradually binds the dissolved magnesium into flakes of sediment. While the reaction continues, large mixers move through the pool, sometimes resembling windmill blades, only turned horizontally. They stir the liquid almost silently, so the sediment forms everywhere rather than clumping together in one spot. When the particles become heavier and start settling to the bottom, the liquid is pumped into the next settling tank. There it sits for several hours, and the solid fraction slowly settles, forming a dense layer that looks like wet cement. The upper part of the water is drained back into the sea or directed for retreatment, while the sediment is collected by special grabs or vacuum systems. Then, the sediment is rinsed with fresh water and dried in powerful drying ovens that blow hot air at speeds capable of removing an entire layer of moisture in a minute. When the mass becomes brittle, it's moved to roasting furnaces. Inside, temperatures exceed 1,380 degrees Fahrenheit, and the material gradually transforms into magnesium oxide. From the outside, it looks like an endless white ribbon of powder, being fed by conveyor into the scorching chambers and emerging with a completely different structure. The final stage is electrolysis. The oxide enters sealed high-temperature chambers where it's mixed with salt flux. This happens either in smelting vats or in special crucibles, where the material gradually transforms into a thick, molten mass. The metal chamber walls glow red from the heat, and inside, the molten material looks like incredibly thick, scorching soup. At this point, electric current passes through it. You can only watch through protective windows, because everything inside appears to glow. Magnesium begins separating into tiny droplets that rise to the surface, since their density is lower than the molten mixture. It's collected using special ladles or drainage systems, and eventually the metal accumulates as shiny silver ingots, ready for further purification or casting into molds. In the case of dolomite, everything starts at the quarry, where the rock lies in massive layers. Extraction doesn't look like romantic stone chipping. It's the work of giant excavators, drilling machines, and blasting equipment. First, the rock gets crushed right on site. Massive jaw crushers chew through refrigerator-sized chunks and turn them into material that can move along conveyor belts. From there, the dolomite heads to factory hoppers, where machines precisely meter the flow and feed it into calcination kilns. The kilns work like giant tubes heated to 1650 degrees. Inside, the dolomite slowly descends while hot air, fed from below, passes through the entire layer of material. From the outside, you only see bright bands of glowing metal, but inside, something crucial happens. The dolomite breaks down into magnesium oxide and calcium oxide. After leaving the kiln, the hot mass travels along metal chutes and cools under powerful blasts of air. Next comes the stage where dolomite transforms into something resembling factory architecture. A tall tower with vessels, pipes, and tanks. Coke, or ferrosilicon, is fed into this tower, along with pre-crushed calcined dolomite. This mixing happens in specialized reactors that look like enormous drums, slowly rotating to ensure uniform contact between reagents. Everything appears as a continuous flow of dry, grayish powder sliding into the reduction furnace. Inside the furnace, the temperature climbs even higher, over 2,550 degrees. The heat inside is so intense that everything around glows with a dim red light. Under these conditions, magnesium oxide reacts with the reducing agent, and the metal transitions into vapor phase. This is one of the most distinctive features of magnesium production. The metal evaporates and rises through the furnace, while gaseous particles move into the condensation chamber. The chamber looks like a vertical steel cylinder, with cooled walls from the outside. Inside, magnesium vapors meet the cold surface, and the metal condenses as a shiny coating that resembles silvery frost. This coating gets periodically scraped off by mechanical scrapers or robotic manipulators operating in an environment with minimal oxygen access. The collected metal goes into protected containers, where it's melted again to remove residual impurities. The melting crucibles look like deep wells filled with glowing silvery molten metal, and extraction systems constantly work above them, protecting the metal from contact with air. The process ends with casting into molds, where magnesium cools and transforms into ingots. Each ingot represents the end of a long journey, from stone extracted by explosions to metal that emerged through evaporation and condensation. Global magnesium production holds steady at around 1 million tons per year. China supplies roughly 85% of that volume, while the United States, Israel, and Kazakhstan handle the rest. Interest in the metal grows annually because the aerospace, automotive, and electronics industries are hunting for the lightest materials possible. For example, using magnesium alloys in transportation cuts component weight by 20 to 35% compared to aluminum. That reduces fuel consumption and boosts overall efficiency. In electronics, magnesium shows up in laptop casings, camera bodies, and smartphones. It's not just light, it also absorbs vibrations well and dissipates heat effectively. In the United States, the share of magnesium in automotive parts has climbed from 3 pounds per vehicle 20 years ago to over 12 pounds in current models, and that figure keeps rising. Despite magnesium being lightweight, flammable, and extremely reactive, it's incredibly difficult to replace. It has a rare combination of mass, strength, and reactive properties that make it one of the most important structural metals of our time. And even though humanity has been producing it for only a century, the potential for its use hasn't come close to being exhausted. If current trends in aviation and electric vehicles continue, analysts predict global demand will reach 2 million tons within a decade. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean? And that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges, using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws, or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed. Diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Every year, the world builds massive icebreakers and liners that weigh as much as entire neighborhoods. But did you know their heart no longer beats inside the hull? Engineers took an insane step. They ripped out a 30,000 horsepower engine, capable of powering a city of 25,000 people, and dropped it straight to the ocean floor in a steel capsule weighing as much as 2 Boeing 747s. This is an incredibly complex mechanism, where a rotor misalignment of a fraction of a millimeter can tear metal to shreds. Watch this video to the end, and you'll discover the shipbuilder's biggest secret. What fatal assembly mistake they hide underwater forever, and how an invisible enemy can destroy this beast in just a couple of days. From the outside, it looks like a massive metal tail bolted to the bottom of a ship. But inside, a full-fledged electric motor. They don't install it in the ship's hull, like they've done for decades. Here it's the opposite. The motor is immediately submerged in water, hermetically sealed in a steel casing, and made to work right there in the ocean. That's why this design is treated almost like an underwater vehicle. The idea to move the engine outside the ship's hull appeared relatively recently, although engineers themselves had been thinking about it for decades. Back in the mid-20th century, shipbuilders tried to get rid of long shafts, gearboxes, and complex mechanical transmissions that took up enormous space inside the vessel and lost part of the power. The real breakthrough came in the late 1980s, when Finnish engineers working on icebreakers for northern seas proposed a radical solution: relocate the electric motor directly into a rotating pod beneath the hull. The concept was developed by specialists at a shipbuilding company searching for a way to make vessels more maneuverable in ice. The first experiments looked risky. The motor needed to be completely isolated from seawater and made to run for years without maintenance. In 1890, the first working units appeared, and within just a few years, the technology started being installed on actual icebreakers. When it became clear that the rotating thruster allowed ships to move in practically any direction, cruise liner builders quickly adopted the system. Since then, this design has gradually changed the idea of where exactly a ship's heart should be located. Not inside it, but directly beneath it. From the outside, it looks like a massive metal tail bolted to the ship's hull. But inside is a full-fledged electric motor. It's not placed in the ship's body, the way it had been done for decades. Here it's the opposite. The motor is immediately lowered into the water, sealed hermetically in a steel casing, and made to operate right there in the ocean. That's why this structure is treated almost like a submarine vessel. I walk past sections of the hull that, just a few hours ago, were separate steel plates, each one several inches thick and weighing thousands of pounds. These are curved metal sheets several inches thick, already pre-rolled, so the future capsule will have a smooth, streamlined shape. Cranes slowly lift these elements and bring them together, like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld goes. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, going over every foot of the joint several times. First, the inner seam is formed, then the outer one, after which the surface is ground down so no protrusions remain that would create water resistance. When the hull closes up, it already looks like a smooth steel torpedo. After that, inspection begins. The seams are examined with ultrasound and X-rays, searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and welded fresh. Then the capsule is sealed and pressurized to levels way beyond what it'll face underwater. If there's a weak spot anywhere, it'll show up right away. Only after that is the hull cleared to handle years of work in cold seawater and constant ice impacts. Once the steel capsule is fully welded and pressure tested, they need to install the electric motor, the main power source for the future vessel. And that's when you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform and looks more like part of a power plant than ship machinery. Its diameter is nearly 10 feet, and it weighs so much that regular lifting equipment isn't even considered. Only heavy overhead cranes do the job. The rotor, the rotating part of the engine, gets lifted separately. This massive metal ring with copper conductors weighs more than a fully loaded truck. The crane starts moving so slowly, it's almost invisible to the eye. The operator works off signals from several engineers standing on different sides of the housing, constantly monitoring the component's position. There's no room for sudden movements here. Even a fraction of an inch displacement could mean misalignment that'll show up during operation as severe vibrations. They literally lower it inch by inch, constantly measuring clearances with laser instruments. Bearings and support elements are already installed inside the housing, and all of them have to align within thousandths of an inch. If the engine shaft doesn't line up perfectly with the geometric center of the capsule, rotation will create an imbalance. After the rotor's been set, engineers won't let that crane move for a long time. A whole series of checks begins. They measure alignment, hand rotate the shaft several times, listen for the sound of metal contact. Sometimes they lift the engine again and adjust its position, spending hours on just a few millimeters of shift. Everyone here understands that once the casing closes, there's no getting back inside, so perfect precision matters more than speed. When the engine finally settles into place, the whole assembly suddenly looks complete. An empty steel shell transforms into a real powerhouse. This is the moment you could call the birth of a system that will soon spin a propeller, turn a multi-thousand-ton vessel, and run for years underwater, where no human will ever see it again. And so more people can see my channel, please subscribe and comment on the video. Modern installations can pump out up to 22 megawatts of energy. That's equivalent to over 30,000 horsepower. For perspective, one of these engines could power a small town of 25,000 people. A fully assembled installation, engine and propeller combined, can weigh over 320 tons, or more than 700,000 pounds. That's the weight of 2 Boeing 747s. The propeller attached to this pod often measures over 22 feet in diameter. Each blade on that propeller weighs as much as a full-grown elephant. Once the engine is securely tucked inside its steel casing, the moment of truth arrives, mounting the propeller. If the pod itself is the muscle, the propeller is the hand pushing against the water. And here we circle back to those head-spinning scales. Each blade is forged from a special alloy of bronze, aluminum, and nickel. This metal has to be strong enough not to bend under thousands of tons of water pressure, yet smooth enough not to create unnecessary turbulence. The blades arrive at the capsule on special pallets, each one wrapped in protective film like a piece of jewelry. Installation is done using hydraulic pushers. The propeller is mounted onto the motor shaft protruding from the capsule, and here precision is once again measured in thousandths of an inch. Any misalignment will cause the propeller to vibrate at high speed, and that vibration will simply destroy the engine bearings in a matter of days. When the propeller finally seats into place, it's secured with a massive nut tightened with a force that's hard to even imagine. After that, a streamlined cap is installed on the propeller hub. This ensures the water flow past the propeller stays perfectly smooth. The entire assembly is then coated with a special paint that prevents marine organisms and barnacles from attaching. Because even a few inches of buildup on the blades can reduce engine efficiency by 5 to 7%, which translates to losses of hundreds of thousands of dollars per year. Every single second, over 100 tons of new trash gets created around the world. Think about it. While you're watching this video, an entire truckload of waste appears on our planet. Where does it all end up? For years, the answer was simple: China. That's where Europe, America, and Japan shipped millions of tons of used bottles, paper, and scrap metal. But one day, China said, "That's enough." And suddenly, the world faced a garbage meltdown. But here's the mystery. Why would a country that banned importing other people's trash start searching for it just a few years later? Stick around till the end. You'll discover the secret that flipped the global recycling industry upside down. For many, many years, the entire world, especially wealthy countries in Europe, America, and Japan, got comfortable with a very convenient setup. They'd collect their trash, old plastic, paper, scrap metal, and simply ship it off to China. Massive container ships sailed across the oceans, loaded with tons of used soda bottles, old newspapers, and broken toys. China was like the world's global trash can. But not just a can. It was also a massive recycling operation. Chinese factories would take this waste, sort it, process it, and turn it into new products that they'd sell right back around the world. It was incredibly profitable for China. They got cheap raw materials and created jobs. And for other countries, it was perfect. They got rid of their garbage problem for relatively little money. Everybody was happy, right? Well, almost. But then, around 2018, China said, "Enough." Imagine a huge meeting of Chinese officials where the decision rang out: "We're done accepting other people's trash." They called this policy, very characteristically, National sword. It was like if your neighbor, whose garage you'd been dumping your junk in for years, suddenly said, "That's it, take it all back. My garage is full and I'm sick of this." And that's when real chaos erupted. Countries that had been carelessly shipping their waste to China for years suddenly found themselves with millions of tons of garbage with nowhere to go. Picture this. Warehouses across Europe and America started filling up with mountains of plastic and paper that were supposed to sail to China, but now had no destination. It was a genuine shock to their recycling industry. What were they supposed to do with all this trash? Dump it in the Pacific Ocean? Toss it in deserts like in post-apocalyptic movies? Of course not, but the panic was massive. Some countries started burning waste in incinerators, which isn't great for the environment since it pollutes the air. Others scrambled to find new trash cans in Southeast Asia, Vietnam, Malaysia, Indonesia. But these countries quickly started pushing back too, because they didn't want to become the world's dumping grounds either. But here's where it gets really interesting. While the world frantically searched for somewhere to shove their plastic mountains, China started feeling a strange hunger. A hunger for plastic, a hunger for waste paper, a hunger for scrap metal. Seems impossible, right? A country that generates the most trash in the world suddenly experiencing a shortage of it? It's like a millionaire who suddenly went broke and is now searching for loose change under the couch cushions. The thing is, Chinese industry had gotten hooked on this imported high. Recycling plants, of which there were, to put it mildly, plenty in the Middle Kingdom, had gotten used to working with cheap, abundant, though not always quality, imported waste. Imagine a huge factory that processes tons of plastic bottles from Germany or the US every day. Its conveyor belts ran non-stop. Its workers knew their job. Its owners counted their profits. And suddenly, bam! The tap of imported raw materials got turned off. National Sword didn't just cut off imports. It left this entire massive industry without its usual food supply. Factories stood idle, capacity sat unused, and business owners pulled their hair out. But why couldn't they just switch to their own Chinese garbage? After all, there are billions of tons of it, right? That's where the devil's in the details. The problem isn't the absence of trash altogether, but the absence of quality, sorted, clean raw materials. The problem is that Chinese citizens don't know how to sort trash. Imagine this. People lived for decades, just like we used to, following the principle of everything in one bin, then off to the dump somewhere. That's the easiest way, you gotta admit. No need to think about anything. No need to separate anything. Just toss it and forget it. And this system that formed over generations, this habit that took root deeper than the oldest tree, suddenly turned out to be wrong. The Chinese government, facing these trash mountains growing faster than bamboo after rain, decided, yeah, this has to stop. We're starting to sort. But something went wrong. Sure, in big cities like Shanghai, where millions of people live in tight quarters, they started implementing mandatory waste separation. Imagine, now you don't just throw out trash. You have to divide it into 4, sometimes 5 different categories. Wet waste, dry waste, recyclable waste, and hazardous waste. And all this has to be thrown out at strictly defined times, in strictly defined containers. But that's just the tip of the iceberg. First, even what gets sorted often doesn't meet the cleanliness standards required for recycling. Imagine a plastic bottle you tossed in the right container, but it was poorly washed and still had yogurt residue inside. Or a pizza box soaked with grease. Things like this, if there are too many of them, can ruin an entire batch of raw materials, making it unsuitable for recycling. Recycling plants that previously worked with more or less standardized imported plastic that had already gone through initial sorting abroad suddenly faced Chinese reality, a mixture that requires additional, expensive cleaning stages, or simply gets rejected. Second, logistics. Collecting billions of tons of trash is one thing, but collecting it in such a way that it reaches recycling plants as clean, sorted raw materials that can be economically viable to recycle. That's a completely different story. In many areas of China, especially in smaller cities and rural areas, the secondary raw material collection system is still very primitive. There, trash is still collected haphazardly, and sorting often happens right at the dump site, by hand, which hardly guarantees high quality. But there's another interesting angle here. China is a country that's constantly trying to upgrade itself to become a leader in everything. And with trash recycling, it's the same story. After National Sword, they decided, okay, if we can't import, we'll build the world's best system ourselves. And they started building, modernizing, investing. New, modern, high-tech recycling plants appeared. They're equipped with the latest equipment, capable of processing massive volumes of secondary raw materials. But they need these raw materials. Clean, quality, preferably pre-sorted. And that's where the paradox emerges. There are plants, there's technology, there's the will to recycle, but there's not enough of the right trash. Picture a giant gleaming factory where robots work, but the conveyor belts move sluggishly because trucks haven't brought enough quality plastic. Or they brought it, but it's so contaminated that it has to be sent to the landfill instead of being recycled. It's like building a luxury restaurant with the best chefs, but having a shortage of fresh ingredients. This hunger for trash isn't just an economic problem, it's also a driver for further change. It's forcing China to accelerate reforms in waste management. The government is putting even more pressure on cities to improve their waste separation and sorting systems, educate the public, and implement fines for improper sorting. New logistics chains are being created for efficient collection and transportation of sorted secondary raw materials to recycling plants. Systems based on artificial intelligence and robotics are being developed for more accurate and efficient trash sorting. Imagine sorting robots analyzing every piece of plastic, determining its type and cleanliness. China aims not only to recycle, but also to use recycled materials in its own production, thereby closing the circular economy loop. This means that a system that previously relied on external sources of raw materials now has to completely reorient itself to internal, more finicky sources. And this trash hunger paradoxically pushes China to finally build a truly efficient and environmentally responsible waste management system. It's like a dragon that created a problem for itself just to heroically solve it later. And who knows, maybe in a few years, China will be not only the world's biggest trash producer, but also its biggest and most efficient recycler. That's the tangled but fascinating trash story from the Middle Kingdom. "70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains. And plastic, if we're being brief, is just very long chemical chains. Break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil. The exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice? Wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building. And inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me. Sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in, oil yield drops to 0, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel. Every 3 seconds worldwide, a new engine block rolls off the production line. The heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened, and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block. Massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious, cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch. A metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's one railroad car. One single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6. If you count one in China, that nobody talks about openly. Fewer factories than NFL teams. And here's the thing, this same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons, 600 times more than zirconium. 600. That makes hafnium the emergency brake of every nuclear reactor. Control rods, the metal plates that slide into the core to kill the chain reaction, made from hafnium. When something goes wrong, hafnium rods drop in. They absorb every neutron in their path. Reaction over. American nuclear submarines run on hafnium control rods. Compact, reliable, no second chances needed. Now here's where the money starts burning. To make nuclear-grade zirconium, every trace of hafnium must come out. To get pure hafnium, it has to be stripped from the zirconium completely. Both processes happen at the same plant. Both are brutal. Both start with sand, a specific mineral pulled from beaches in Australia and Africa. What happens next involves 100 repetitions of the same chemical trick and a column of machines taller than a 3-story building. Raw material, zircon sand. Looks ordinary. Slightly heavier than beach sand, faint metallic shimmer. It gets processed into zirconium chloride, a powder that acts like salt with an attitude. Sucks moisture from the air so aggressively that workers handle it in climate-controlled dry rooms. The hardest part comes next. Liquid-liquid extraction. Dissolve that chloride in water. Add an organic solvent. The two liquids grab zirconium and hafnium at slightly different rates. Hafnium moves a tiny bit more into the organic layer. Zirconium stays in the water. A tiny bit. That's the problem. One pass does almost nothing, so they repeat it. 50 times. Sometimes 100. 50 separate extraction vessels chained together in a column the size of a warehouse wall. Liquid cycling back and forth for months. The electricity bill alone would make your eyes water. A single solvent leak shuts the whole line down for a week. Picture a 100-step coin sort where heads and tails are almost the same weight. That's what this machine does. And it never stops. After 100 cycles, hafnium comes out as a chloride compound. Still not metal. Turning it into metal requires temperatures that would melt most equipment. Hafnium chloride gets packed into a sealed vessel with chunks of magnesium. Temperature climbs to 1650 degrees Fahrenheit. Magnesium rips the chlorine atoms off hafnium and bonds with them. What's left behind is pure hafnium. But it comes out as a rough, grey, porous mass. They call it hafnium sponge. Looks like pumice stone someone left in a furnace. Pick it up and it feels heavier than it should. That ugly grey sponge costs over $1,000 per kilogram. More per ounce than gold at certain market points. And it's still not ready for a reactor. Only a handful of companies buy it directly. Framatome in France, Westinghouse in the US. Shipments move in sealed containers under strict tracking. Lose a batch in transit, and people in government offices start asking questions. Vacuum arc furnace. Temperature above 4,000 degrees Fahrenheit. Hafnium melts at 4,050. At that heat, it reacts violently with oxygen and nitrogen. Even a breath of air inside the furnace makes the metal brittle and useless. So the chamber is sealed, air pumped out, replaced with argon. No oxygen, no nitrogen, no room for error. First melt produces an ingot. Composition isn't uniform enough, so they melt it again. Sometimes a third time. The final ingot weighs 10 to 20 pounds. Gray, shiny, looks a bit like stainless steel. Think about what it took to get here. 1 ton of sand, 100 extraction cycles, a magnesium reduction at 1650 degrees, 3 passes through a vacuum furnace above 4,000 degrees, all for a 20-pound bar of metal. That bar still has to prove it's clean enough. In a nuclear reactor, almost pure and pure are two completely different things. Nuclear-grade hafnium must contain less than 1% zirconium. Zirconium isn't toxic, it just lets neutrons pass through. If a control rod has 2% instead of 1, it absorbs fewer neutrons. Under normal conditions, nobody notices. During an emergency shutdown, when every neutron counts, that extra percent could mean the rod fails to stop the reaction in time. 1%. That's the line between safe and not safe. Every ingot gets mass spectrometry analysis. Every batch comes with a chemical passport. The buyers don't take the factory's word for it. Government nuclear programs, defense contractors. They run their own tests in independent labs. Zero trust. The cost of a bad batch isn't money. It's a reactor that won't shut down when it needs to. 5 factories on Earth can meet that standard. And now a second industry is pulling on that same tiny supply. Since 2007, hafnium has had a second life. Inside microprocessors. When transistors shrank below 12 nanometers, the old insulating layer stopped working. Too thin. Current leaked straight through like water through a cracked pipe. Hafnium oxide solved that. A few atomic layers hold the charge where silicon can't. Every modern processor contains hafnium. Phones, laptops, data centers. Microscopic amounts, but across billions of devices, it adds up. A second major buyer pulling on a supply that fills 1 railroad car per year. 1 factory down for maintenance can move global prices. 2 offline at once, and both nuclear and semiconductor start making uncomfortable phone calls. There are no hafnium mines.